We still have about 5 minutes, so waiting few more minutes. Form to fill or okay, this quite a lot. Oh, okay, I know. It's okay. Yes, one more minute. Can I have one? Thank you. Okay, I think probably is the time now. So good morning, everyone. This is the last lecture, I think. I hope you enjoy the course so far. So this last lecture of mine is not the last lecture for this course, but for me, actually, it's on the application of the physics informed machine learning and digital twin for additive manufacturing. And then, as I promised yesterday, it's more about the data-driven or machine learning based example that we apply to design a new material that I show you, actually nickel and also titanium a little bit by alloy design. But before that, I want to talk a little bit about what is a digital twin and what is the use for additive manufacturing. So now a lot of research has been going on to basically identify the challenge and the way how can we move forward, identify the direction strategy from interdisciplinary consortia to basically move the boundary, move the technology forward, especially for metal additive manufacturing. So if we are looking around in the a paper or in the outlet, media outlet or whatsoever, you may see digital twin like this. That's data-driven for maintenance. Actually, for let's say in a jet engine, you want to understand what happened during the operation, and then you want to have digital or physical and digital twin running at the same time to understand what is the problem during the flight. For example, that is the example that a company like Rolls-Royce trying to do it for a number of years already. It's not just happening doing it now. So the attribute of digital twin is just a virtual representation of the real world component. Again, they have some key feature that we need to understand, which is the feedback data from, and then correction of tests, and on the computer, and they provide value that you can simulate, analyze, or optimize. And this represent data of the physical asset that we are looking at here will produce a kind of perfect, hopefully, a physical product that we can use in service. But it's not just in service, but for manufacturing purpose. We may looking at something a little bit lower length scale in terms of production of the sample, for example. This is a concept of digital twin where you have a hardware here, physical twin, and you feed the real-time data, such as the data for the sensor, and then to the digital model here that you may use the surrogate model that I showed you before, machine learning predictive model to forecast or do some anomaly detection, for example, and then use AI analytical capability to feed back the real time to control and command what happened in the physical world. That we talk a lot about sensorization, about CNC hardware, software driven, or whatsoever this may be, the 3D printing machine. And this actually, we in order to summarize this, we have digital twin actually considered as a physical entity of the virtual replica in the two-way digital data that communicate each other. So that means the key is the communication between the physical and digital model, which are predictive capabilities that I will show you a little bit later what is that. And leverage this process intelligence to capture digital model using faster solving surrogate. That means what this may be replaced by the surrogate model may be replaced by, for example, reduced order is this kind of surrogate model that we have some quality control aspect of the product, for example, for the physical entity. This surrogate model create using, as I said, data-driven or machine learning. Talked before from experiment, digital model can be physics-based or statistical-based. Physics-based is what we talk a lot, and then statistical-based, probably the data come from experiment, for example, that you can feed into the digital model here. And give example of the benefit of this process, digital twin, is will deploy in anomaly detection, correction, and then diagnostics, causal process control. And that is actually what we want to do, is our vision to make it happen in the near future. So actually in manufacturing industry, so I'm trying to see some broader view and then try to narrow down to the uh, what something related to us. So the achievement of this one or will lead to improvement of the product quality and process productivity. So using digital twin here, that means you use the digital computer for simulation and manufacturing process. This will need to understand the process, because the causal relationship will enable us to improve the quality of the product that we need. And another aspect is we need to use something, not only digital computer, also need to use digital sensor to implement digital control, because this will actually generate some data for us to feed into the model that will make us actually try to, again, as you see, the data that feed into this here will need to be from sensor maintenance history or whatsoever, that from physical model here feed into digital twin, which is, kind of digital model. Whether or not you use data analytic, machine learning, or physics-based model or statistical model here, and then you feed back your control command back to digital twin. And these will be interacting with each other. So definitely there will be some virtualize or analyze offline that you can use to control this remotely. So I see some evidence already from a lab in field lab, around the world. For example, I just visited Japan early this year, where they can control what happened, or some simple operation in the lab, which is quite amazing to run 3D printing, for example. Yeah. So another one is adopt the programmable logic control-based feedback control automation in factory, that you can actually resulting in energy scheduling, that sometime in a company in US, a steel company, that they use a digital twin or digital model to basically calculate some, a flow of material in the factory, and then try to schedule the time for the right spot for the electricity cost, that they can minimize significant number of money, in terms of millions, something like that, by actually use some digital system that they can allow this to happen. So cost reduction is the goal, and increase the productivity of the part. So now this is a bit closer, so narrow down to the kind of robotics, additive manufacturing, like arc welding, for example. You may implement some sensor and digital model here, and material model is so important, and rule models. And this is something that we feed into the data, that we can actually get some production or the machine tolerance and feedback into the decision making into the physical entity. Again, this is I would say in the virtual world, or the modeling things is the brain for for the digital twin. So whether or not we can collect this on fly, that's a purpose, right? We want to do something without any defect and without any waste and wastage. Yeah. So it's quite a lot of text, but I think it's useful to highlight some of that. So you can find this information more from the journal physics that I show you here, journal physics material here. And they, another characteristic for the process digital twin for AM is actually with supervisory capability, that you can use the digital twin to offer virtual emulation or animation to support understanding of statistic or dynamic operation characteristic. For example, you can use this to plan and test the impact of critical scenario or conceptual business model. And this digital twin process, digital twin with the diagnostic and control capability, this is something is closer to us now, with the support optimization of real-world assets and process performance. And this will link to the sensor data. So diagnostics or control capability, this is actually something about sensorization, using sensor to measure it. And process digital twin with the predictive capability, this is something for the predictive simulation that we are talking about in terms of the quality control that we looked at previously. So the application of this in AM is actually start to find is used more and more now. So if we looking back a little bit, so we use predictive capability here to basically what we want to get is actually decision maker for the test and understand the impact of scenario here. What is the best, how we do it, what is a dynamic model that we can use in the real operational processes. That's pretty much the characteristic of the digital twin with different capability that give rise to different, character for the model. So this is come closer to the 3D printing. So application of what we call closed loop control. We close from digital and physical world here, and the different components that contribute to the construction of digital twin. That I think I may start from this one, which is actually not really a part of that. So you have printed part, and then you have printing machine, 3D printed machine here. So this is something you may need to run. This is a physical world and this is digital world, right? In this digital world, on your laptop or whatsoever, you have mechanistic model running the mel pool simulation, something like that, or rapid kind of calculation. And then you have statistical model. That's why I said this is a missing part that we not talk a lot in the result that we get. We just run for the sake of simulation and not actually take care of how can interpret the data. So interpretation of the data is important. And then you have a model that have a control model again. So you try to link this together. And then this is a process variable that you may try to predict to the physical world here. And data from the physical world can fade into, by sensing and control, back into the digital model. But I mean, beneath that, you will need to have the model use this one to train the machine learning, because you not be able to actually run every condition on fly. It's impossible. It has to be another layer of machine learning using neural network training here, and then you update the model and feedback. Or probably, I mean, this one maybe come from model or experimental data, large data set that you have. And then you get this simulation result feed into the data that you have here. And then trying to, or these data may come from experiment, from censoring data, testing, literature, classified data feed into this one. And again, this is still a conceptual diagram. It's not, some people try to create a flow chart for a particular scenario, but again, this is just conceptualized diagram that see how things work in research in digital twin for additive. So this one has been done, the characteristic of the application of closed loop control in this one, usually done to gain the process repeatability. Definitely now, everything is stochastic in additive manufacturing. So we need to make it actually more repeatability in the AM part here. And this will be possible for manufacture safety or mission critical part with guarantee minimum quality level. Actually, this is important. So we're not going to do digital twin for just this is digital twin. It has to be some important part that we are selected to do that. That's why I keep saying at the beginning that material process and application is come together as a package that you are looking at. So passport that you want to do. And then this is improve the product integrity for sure. And this because you don't want to reduce any necessity to cut the sample and then to see. So you want to basically, if possible, we want to do in a non-destructive testing. That is the aim, right? And we can feed the sensor back to the digital model. There's some research going on in this physical here on the sensorization of the non-destructive testing using some kind of vibration or whatsoever, that you can feed or generate the data as quick as possible to understand the defect content in the part that you have. So this is a way people doing, I mean, I'm talking about people in system engineer that we're trying to do something on in this one. So equally, the quality assurance of process product is something that we need. I mean, we need to find because this system has to be certified as well for standardization, and then, I mean, with the pass certification. And another quality control to assure quality of product is actually we need to reduce some weightage or some scrap as all possible. So ability to determine optimum process condition. Again, that's what we have been talking about the brain of this digital model here on the to eliminate trial and error experimentation. And we'll build this right first time and every time, because every time you do it, it will be right first time for that condition. So there's no longer something that this change the practice that we've done before, that we know in a very controlled manner for casting or forging. But this is quite stochastic. So that's why part will be built right first time every time. So there is another conceptual idea for digital twin that I think this is much deeper in the things that we have discussed in the past 4 days. You know that, I mean, definitely the brain of this is lying to the physical-based simulation that we talk a lot, and then, but the important part here is actually you have the physical part, manufacturing, and physical-based simulation up there, and across the length scale you transfer the simulation validation of data flow here, and you have sensory measurement and data feedback, the loop here across the length scale. As I said, this is a 3D printing now in micro length scale in the melt pool, meso in the layer wise, and then 3D printing level in the part or defect, something like that. So this may be an input, the geometry of the 3D printed part, powder material property, and then laser fusion parameter, monitoring and measurement here. And output will be defect content that we said before, grains, growth, and microstructure, stress and strain, distribution, distortion. And we want the output of optimized parameter. And this will be used and controlled if we can understand and then get a robust model that can give us some predictive capability with rapid calculation. We can actually, that is the ultimate goal with the data-driven that we want for 3D printing. And that actually has some kind of more specific example in the in this kind of finite element calculation here. And then you use some powder properties, some way, somehow you treat in your computational grid. Here, there's some material actually heating, some material actually already heated. And then you will try to predict something that you can use pyrometer camera to detect the melt pool size, and then to compare again the simulated data from finite element analysis. So you will see here that the grid of this simulation is not good enough, but actually if it's working, it's okay, because we want to make sure that we not actually compromise with the accuracy of the of the model, but at least we can extract some important feature from the model that can predict some important things, like we discussed yesterday, that temperature field may tell you a lot of things about from porosity, as well as the property or microstructure and property that we discussed yesterday. So, but this one is not possible, only the physics-based model. I mean, I hope you appreciate that. Because they have another computer science related layer that we are talking about. So even we have here, we will have the cloud layer, which is about the data analysis here, cloud data processing and application. Again, this is a bit far from what I'm looking at, but we're looking at machine learning or big data analysis, something like that. So we are in the processing step, and then we need to link with the monitoring system. Again, this is another flow of data, and then the machine level that we need to look at, and collaborative of this data across the different layer here will be needed to be constructed to successfully deliver the digital twin for particular machine and process considered. So I think it's quite broad and give you some context about what is a digital twin and what is needed to be done to achieve to that point. But what we're going to do here, how can we actually use some application of the data-driven to do something that we can get the product. Let's say input is actually the parameter composition or whatsoever, and output is a new composition. How can we actually collect or adjust the composition or apply something to additive manufacturing? I have to say that I don't have example in terms of digital twin system to show you, but I can show you some application of machine learning that we use to do something with, and then you get a product which is a kind of new powder composition that we use. So it will be based on the physics-based model that we discussed in the past few days. And this is the case for we call material design and process design for titanium alloy that we try to do since 2013. So it's a large collaborative effort. So you may know that, or may inspire from titanium is not only used for aerospace but also in biomedical application as well. So the problem actually, I think probably Professor Kumar already tried to solve it. So there's a problem that there's a big mismatch between metallic bone and because we in the metallic implant we use we have the bone with different stiffness or modulus here. I mean, let's say conical bone or cancellous bone here. They have quite low stiffness compared with the organic bone, the real bone. So the way they try to do here, try to design using additive manufacturing to design engineering structure that allow them to change basically the stiffness and the strength of the material that match to the bone for implant application. And this is something, if you look carefully, this paper try to show that the different design of lattices that they call meta material. Actually, this is 5-6 years ago. You will see that you can actually going closer to the real modulus here. But again, it's still not too close. But how can we translate this idea and materials research to the real application? That is the thing. So in order to do this, what they do is actually they use the alloy design framework. I mean, this so-called alloy by design for titanium. I mean, to borrow the concept here from the aerospace alloy design that can identify the phenomenon in the physics, what happened in the gamma beta stable superplasticity here. I mean, this is for, again, just emphasize it's not for implant, but borrow the concept from this one to optimize the low cost formable alloy with the, again, they call ABD still, alloy by design, with the cost, strength, stability, density, and formability here to find a new design space. Again, they use the same concept to consider cost of the material. Density should be not too dense and not too low, and then normalize diffusivity, strength of azimuth index to basically try to respond this. And then you map the new alloy composition by considering this into the design space here, and then try to rank and also select some window that allow you to do some process specifically for the application you are looking at. So in this case, this is a superplastic forming in the fan turbine blade. So when we'll need a working window for this, they know. So this may not be able to apply directly to the implant, but there will be some example to show you. So let's say they know the window that give rise to the optimized condition for that. Again, this is based on engineering selection. It's not just the data as a data. You need to select this based on some physics-based understanding or physics-based modeling that allow you to select the right window to cast or to produce the material. And this actually, in the backbone of this one, we also run some model in the background. So that's why it's actually titanium 6.4. Looking at this since 2013 on the particle level, molecule level, microstructure, and macro scale. So we will combine the material by design here with the process by design. So we'll try to use the framework that I mentioned earlier, that we use the thermal fluid flow for the melt pool, and then grain growth model to understand the microstructure, and hence another solid transformation as well. So give you some idea as a picture here. So if we apply previous one with additive, so we start optimize with DD process, for example, and looking at the microstructure evolution at the representative number of layers of deposition here for design a new material. And then we need to use this microstructure informed framework here, physics-based machine learning framework, to input the data to using thermoclock here, output as a, so we'll have input and output as a phase equilibrium or intermetallic transformation, temperature, solid solution strengthening, all the physical parameter that you are looking at. And then we input this process variable from whether or not you use PBF or DD, and then trying to use the a number of platform, CFD, CA, DIGTRA, Prisma, to produce or to calculate the thermal cycle kinetics and then microstructure information. And after that, you use this microstructure information in terms of the everything you have as an input to use the property prediction platform to mechanical property. And that has to take into account the fact that this process is so kinetic. So we need to understand how different that we may anticipate it from the process before. For example, that what we talked before about freezing range or the change in the solute segregation will be considered. So that is the conceptual diagram that we try to draw here. Like you will not actually go to this pathway easily. Like in your alloy design, you may need to adjust your inside merit indexes, or basically the criteria that you use, considering these kinetics that are induced by the AM, additive manufacturing processes as well. And this will feed into the alloy design or data-driven machine learning framework that mentioned earlier. And this is how we feedback or improve the model to design a new product. In our case, it will be new material, new powder, for example. So we also done some detailed characterization and simulation on this as well, on the single track, single track of titanium alloy, and try to understand the alpha beta formation. And then you will see that this is very detailed, characterization and calculation. This is calculation, it's not characterization actually. This is calculated. And then in the 3 layers, so you can understand the effect of the kinetics and also microstructure development across the characteristic, I think, size of the process. So you can actually represent this into the design, alloy design model, and hopefully this will be able to improve the design algorithm and hope we can get better composition, for example, to print better as well as to get better property. After that, we will combine it manufacturing and process design to understand the physical effect in our PBF using uniform powder distribution. So again, this model will be scaling up a little bit now using the interaction of the heat source and model. Maybe you will include the effect of porosity here as well into your study. And this representative model here will be simulated to understand better condition. And I think now I'm trying to show how to link toward digital twin or digital model that we're trying to use. So you will see here the point I want to make is that the length scale here is come from micrometer to about 1 centimeter here. And you see each voxel here that you deposit the material is actually 1 millimeter. So there is a 6 order of magnitude mismatch on the scale here. And how can we represent 1 millimeter with all the information in the lower length scale, 6 of magnitude lower? And this is an important equation actually that we have to understand the melting process in the 1 millimeter length scale. That is the reason why we do 1 millimeter length scale on simulation. Otherwise, if you use the match of 250, but I don't, it's not, 1 millimeter is still too small actually for the big model, right? So 1 by 1 by 1 is still too small. And that is why this is how we choose the length scale of the problem. And even you deposit here, you will see that we need to implement some clever kind of, we call switching function that not assign the homogeneous property in the in the deposition voxel here. It has to be some distribution of property in that we call property switching function. So we need to switch the property at each deposition here differently in order to take to account all the lower length scale information. Still, work is going on. It's not robust. It's not done yet. But we know people around the world, it's not just us, doing the same thing. So they may run crystal plasticity to develop this method in order to allow property to be predicted correctly in the large scale model. So this one, another way we call element birth method actually. So we extend the model here to predict stress and distortion in a component scale. You will see here there is some distortion in the element already. Did you notice that? It's not actually hexo anymore. So we try to incorporate this into the part distortion during deposition because this is the model that we use to digital twin, right? If this one run fast enough, that means in the same time as the way, but time in 3D printing is in microsecond. And how can we run this in microsecond to get the feedback into the digital model, physical model? That is the big challenge and question again. So we have mismatch, we bridge the length scale now, but the next question, how can we use this information and feed back into the physical model with the reasonable time? not in this time, so it's too large anyway. So now we try to bridge to this, but we need to feed back to that. So this is the kind of the real things that I think as an engineer has to work together. This is no way out. If you want to build a good predictive model that can do something or feedback some useful information. Otherwise, you may rely on the sensor data that you get. That means based on the sensor, the predictive capability based on what you measure. It's okay, it's fine. But if you want extra information which not easily measured by sensor, it's probably difficult, right? So you can do digital twin in many ways you want, actually. Or even you can do digital twin for example, I don't know, serial sectioning of something, which is not valuable. But what we do here is about mission critical part that we need to really take care of. And then this may be very expensive part as well. So again, there's some number of drawback and also some challenge, remain challenge that we need to do. So that's why it's still we still have to communicate with the data from the lower length scale to the macro length scale, and then feed this data back and forth. This is maybe small loop control here. And then the new method here, taking into account the component distortion, and then you will see that is actually calculated and also is actually taking into account here. So the material property is important in this case because you need a function that can switch the property considering air and material and powder at the same time in a voxel or in a cell of calculation cell that you do. So again, people trying to do this and try to validate against experiment like we do, we show you a little bit later. So you will know that this will be good. If this geometry is not simple like this, if this is a turbine blade, how can we make sure that we predict something correctly? Otherwise, you will do the we call command. Auto collection wrongly, and that's not good, right? That means you may try to produce something wrong in your critical mission part as well. So we will need to take into account of the lower length scale data. That's what I mean. But now to them try to elaborate more what does it mean by that. So take microstructure data from lower length scale model to include the information to the part scale analysis here. So this is some two different methods that we mentioned that we call element birth and death. And then another one is, that means birth and death does mean one element assign one property. Another one is switching function. That means one element not homogeneous anymore. So you have assigned property into this one. And then we try to compare these two methods together in the part scale analysis. And this is the predicted thermal cycle in the, we do multi-layer deposition as well. So we want to make sure that we can see here the repeatability of thermal cycle in the real digital model we want. So we also validate this with experimental data. But as I mentioned to you earlier, this is the plate that we are looking at. This is the plate here. This is the plate here. So there will be bending. The curve of due to the distortion when you deposit the part. This is the size about 10 millimeter length scale, and this has been done since 2014, actually. So 10 years ago, and then we compare the thermal and distortion for the validation purpose. So we use the data from two methods, which is element birth. That means activate element by element, and also property switching. So we switch the function here. So you will see that property switching function get predicted temperature at the base using thermocouple measurement, very similar, very close to the experimental measurement here. So you will see the thermal cycle start to increase and then decrease like normal. But again, this is have to be noted that this is at the substrate, not in the melt pool. And resulting distortion has been measured based on the calculation and experiment here. You will see that switching function actually a little bit closer than another method. So this gives us some idea and direction to move forward in terms of how to develop this digital model that can capable to predict the part scale analysis there. So this is some initial work that I've done, and then because there is some other colleagues that involved in this kind of work, so I did not say this is all previous. This is not all my work. This is some other people work as well that we collaborate together to bridge the length scale or multi-scale, and then we hope that this kind of approach, as I think this thing is relevant to mechanical engineer as well, that will make us going to the right research direction. So this is more about digital twin using data from experiment and from the model to basically try to predict to create a digital or predictive digital model that allow us to further develop for digital twin. Again, digital twin as a digital twin, I think is nothing without this brain, right? Otherwise, you don't have any capability to do anything. It's just a model to do something which anyone can do, I think. So material data, material information is so relevant. So moving to another, a little bit different, but I may call it material informatics, about the material discovery. It may be related topic as well, if you want, but it's not really digital twin per se, but just want to give you an example that we discussed in the past few days about a new nickel-based superalloy that I'm talking about. I want to elaborate and share you some experience of our journey. I mean, 10, 15 years ago that we tried to develop this, what is the thought behind that, and I believe this is a little bit some history that what we do. So I actually previously I was in the part of the alloy by design for the new nickel-based superalloy here for additive manufacturing. So we published the work after number of years of work in Additive Manufacturing on the alloy by design application to new superalloy for additive manufacturing. The work, this would be a kind of outline of the work here that we do. For example, we call material discovery or material informatics, whatsoever people call it now, but 10 years ago, there is no such a bad word like this. But anyway, 3D printing for material here. We're talking about a several type of material, right? This is about the 4 class of the material we're talking about this day. And this is important because people talking more now about material discovery, material informatics, and that actually what we are doing 10, 12 years ago. So based on what this concept, I share with you the journey, what we do. So we know I will start with background and motivation and challenge in additive manufacturing based on our understanding that time, 2013, 2012. And then we try to use process. We know that it's a process sensitive manufacturing. So we use the process informed design here. And again, have to know that based on the availability of data that time that we have, and we try to design for process, microstructure, and property. Again, in order to close the loop of the PSP, which is processing structure property relation. So this is a bit repetition from previous slide that you've seen before, that I highlight the output, but this is a bit the underlying thought that we hypothesize that we need a new class of material for the new processing approach that we use. So every time we have a new process like forming, casting, or additive manufacturing, whether or not we can use the same material, that is the hypothesis there. And then we said AM will be enabled by development of new generation material. In this case, we're interested in nickel-based superalloy. And then that is another previous slide as well. You will see that there's some challenge because this is a rapid repeat thermocycle process that may induce defect, locally, and then non-equilibrium things can happen. So the challenge is try to control microstructure by processing parameter or processing root here. And we hope that we can reduce some, or we get some property we want, not necessarily to be defect, but about the performing material that can be used for additive manufacturing. So inspired by the performance of alloy, that you may see the AM reduce the creep right by about 1 Lassen-Miller parameter. If you see here, it shows from CM247, which is single crystal superalloy here, 1 order of magnitude. When you change from directional solidification, you will get lower of the creep life here in the Lassen-Miller plot here. And then if you try to do some additive manufacturing in the same material, the creep life actually reduced further to this. So based on available data at that time, and then we compare with MA, MA. This is a cast alloy, which is somewhere in the middle. But if you talk about CM to increment 7 to 1/8 in a rod and AM, it's the same. So the life of the material after printed, again, this is actually as print machine condition, machine at print sample, yeah. So there will be some difference. So another thing is the role of the processing of alloy performance. As you know, they're so very heavily textured based on the observation that everyone know. Isotropic property is all around, and there's some common defect. That time we don't know, we don't investigate totally much on this very much. So lack of fusion, cracking, or porosity usually found in this kind of printing process. And then we try to consider residual stress as well in the new alloy that we're going to form, because, as I said, we need to predict some way, somehow, or have some parameter to indicate what happened after processing this material, like strain edge, cracking, that relevant. That is why. So we try to, based on observation here, the strong texture and residual stress are built up during the process. So what we do, we try to print this nickel-based superalloy in the condition that we believe that is the optimum condition. But still, it's actually, you found a lot of crack here. That, again, I will show you later. We developed this alloy based on the Learner-Shaw 400 AM machine. So you will see that it's still uncoverable interregular cracking is a more critical challenge for this time. Temperature-dependent property here, and cracking found occur everywhere. We don't know very much at that time because what happened, but further investigation has been investigated later. That I showed you yesterday, that solidification cracking try to classify what type of cracking during the material printing here, and residual stress. As well, we done some residual stress experiment and measurement using the bridges structure. So the critical challenge here, we believe the residual stress is facilitate the crack formation at grain boundary, and at the edge, also at the bulk of the material. And then, as you know, if we keep this in mind, in order to develop a new composition, we need to look back a little bit about what we need. And this composition is supposed to use in the high temperature application. As we all know, this is for high temperature. It's not some when I say high temperature, it's performed at least above 850 degrees centigrade or above 1000 degrees centigrade. And then we're focusing on the critical part like disc or blade material. If not single crystal blade, it will be some other blade made from increment 718. And traditionally, we use casting, and this is a kind of composition of the available, and also based on the benchmark actually of the nickel-based superalloy we are considered. So you will see it's about 13, 14 elements that form one alloy system. So this slide, I think I may script this slide already. So this is important. So what we do, the chemical complexity of nickel-based superalloy is an issue. So it's contained up to 13 elements, and limited information related to composition property trade-off are available in literature. There's not much in literature about this, especially information about the damage characteristic in limited number of alloy. It's just CM247, Hastelloy, Inconel 625, Inconel 718, and etc. And that means if you want to vary the composition, I said, if the resolution is 1 weight%, if you have only 2 alloy elements, you already have all 1,000 element choice that you can choose. But if your resolution is 1 weight%, but 6 principal elements, you will have about 1 billion choice to choose. But again, if your resolution, because in nickel-based superalloy is 0.01% is significant to the property. So you may end up with 10 to the power 21 composition. How can we deal with this? I mean, this is already big data for me, if not 100 trillion. I think this is more than trillion, several trillion composition. And the data that we can find from literature is so limited at that time. At that time, there not much paper that you can find from the Scopus database here. So it's just thousands of paper only in the number of AM material. I'm talking about AM metal, AM data that we can find that time. So how can we do this? So this one will need to base on some empirical design. That time we don't do any fancy modeling yet, but we do to some extent. So what we do, we have alloy by design here. So this is a bit material informatics, and then you feed into the small batch of the powder that you can produce. You atomize it, and then you understand the thermal fluid dynamics, I mean the melting, and then we use this machine to optimize. We use a reduced volume build, so with the minimum 1.5 kilo of a new powder that we can use, and then we accelerate the testing by the facility at Oxford to validate the model and then close the loop of the design of the new material. Again, this is a kind of material discovery framework that has been done long time. Modeling, we use kind of modeling in form, but modeling in different length scale from empirical to the physics base, to the alloy development cycle. And this is the alloy composition here we consider with the major property that we can have: creep resistance, oxidation resistance, manufacturability, density, and then material cost, because cost is a big factor for the new design, right? You need to take into account to that. And you have the composition material property relation. But alloy by design framework is a bit different. So we want to understand the design constraint here backward. So, and then we want to work out what is a composition that gives rise to this property. Kind of inward design. In order to calculate this one, we need to design alloy space, calculation of phase equilibrium, calculation of microstructure architecture, that time we call, identify the merit indexes, apply design constraint, and try out some set of design, some set of composition in order to eliminate some trial and error. And that is something we said. This will need to take into account the strength of material, which link to the ABD energy and gamma prime fraction, which is some equation before. This may calculate from first principle calculation with the new composition of material. Again, we link the lower length scale to the alloy design or material informatics here. So you will see this is, if you're not in the metallurgy field, I may explain a little bit more. This material is going to be, has some architecture like this. So gamma prime with different crystallographic structure, kind of cuboidal structure here, which is quite amazing, very ordered structure in the material. And the map here show the composition. And you will see that the activity of the slip system is ABD, antiphase boundary energy, will be on this a slip plane here, and the composition dependent of gamma prime actually has been very important to the strengthening of the material, and that's why this will be considered in alloy design cycle as well, the strength of material. And then we identify the strength of material using these indexes. So you have ABD, which is probably calculated from somewhere else, and then because you need to feed into the design loop every time when you get the new composition. So you have to calculate every time here. Fraction of gamma prime, again, there's some empirical equation you can use, feed back into this, and then you can get, different fraction and, map different energy here in order to define the strength of the material. And this strength of the material doesn't need to be excessive amount of gamma prime, actually. People may think that the more gamma prime, yes, the more strength, that's correct, but we have to find optimum condition to get enough, let's say in composite, not need to be a lot of fiber to get the strength that you want. You may need to find a minimum, upper bound of the minimum level of gamma prime that gives the strength that you require. And next one is consider the process. That time we consider, this is the graph that we conceptually draw, and then you see this happen at this stage. This happen at this stage after heat treatment or doing aging step. And the strength of this will susceptible to fracture. So the fracture or the failure of material need to be considered in the alloy design cycle as well, or we call informatics, whatsoever you call, for additive manufacturing system. So there is that's how I said yesterday about the Incal 718. So we start from what we have, and then based on what we have, we believe in the weldability diagram, but we know that it doesn't have anything doing with the additive manufacturing. But we borrow this concept and we assume that this additive manufacturability actually similar, I would say, to weldability, and this is a big assumption. That's why we follow this kind of diagram to develop some indices for the crack. And then we use crack formation due to the shrinkage as a cooling and precipitation hardening to consider into the design cycle. And then the rate of gamma prime precipitation influenced by the fraction of it. And then the growth. Again, you will see here that is based on the metallurgy. We can call that this is a physics-based informed machine learning that we try to develop here. And then the next attempt, we modify that diagram a little bit. And then we try to say that we want to use this diagram for additive manufacturing. That is starting point of the link composition and processing. And that's we call this criteria as a cracking criteria, as the criteria to determine manufacturability of the material. So we use this one to indicate by the, actually we cannot incorporate at that time thermal signature into the process, but we use these indices that I showed you yesterday to take to account, okay, this may be the crack will define the manufacturability of the process, and this diagram has been proposed. So you can find it in the paper as well if you want. And then that means we can isolate high strength alloy for AM. This is the very first version, and that time this company that I'm collaborate with doesn't call alloy. If you may know there's a company called alloy now, but previously it's called Oxmed. The first generation, you can identify the low and high crack susceptibility. And then this is actually trade-off between resistance to, we still call weld cracking, not AM, and high temperature strength. And that is, we need to consider another factor of certification. Cost, big factor. Oxidation, thermal diffusivity, density, fatigue resistance, thermal expansion in the design cycle loop, in the material informatics loop here. And then we can generate the different ranking at different, because the screening of this based on the metallurgy that we identify the window for different, let's say this is a more mass fraction of gamma prime at 900 with strain edge cracking. Strain edge cracking, because we're talking about cracking at that time, and thermal temperature, creep life at 1000 degrees centigrade at 137 megapascal. And this, again, there's so many indices that we use to screen out and then identify the window for the new composition that we want. So this is how the alloy design framework has been created. And then all of these results here, you can find it in literature. And next is about once we get that composition, what we can do, how we do it. We need to prototype this alloy manufacture using atomization, right? So you will know that this is basically alloy composition that manufacture using gas atomization. We use the industrial practice atomization to produce the new composition that we found. And then at that time, we all know already the hurdle for this processing. You have trap porosity, microstructure, even dendrite, something like this. And then we run simple. That time it's not very fancy, simple, but give enough information for us to know important of the parameter of processability to the new alloy that we are going to develop in terms of porosity that may lead to crack or surface morphology at different conditions compared with traditional alloy. And we then do the printing basically at a selected condition, and using this, as I said, it's developed using Renishaw ABD alloy series using Renishaw AM400. So I think every time when people talk, I have to mention about machine, because AM is a machine-dependent process. Which machine you develop this alloy, you will need to use that. Yeah, so basically we can get the best processing window, and that is the best condition up to now. Just want to feedback. I hope this is a closed loop control. Feedback to yesterday talk that is the condition we use to print those 4 alloy to study the cracking, if you remember. Yeah. So we print this and model to inform the choice of process parameter. Again, you will appreciate that this is not just happened by chance. It's actually very well systematic. At that time, we do some simple grain growth model as well to understand the microstructure of the function of the parameter that we optimize. And then we check the printed condition. Again, this involves not only modeling, but also a lot of experimentation that you can see what happened. And then we found that time that there is no gamma prime forming in this new series of the new composition we're looking at. So it's supposed to have at nominal composition at 25% gamma prime, but we found no gamma prime during even prior to heat treatment and in as printed condition. A solid solution. And then why the new alloy is actually manufacturable. This is the question. That's the beginning of the work of in the following work actually that we do. So you can know, I don't need to repeat what I said yesterday. I think you will see there's no crack, and then we try to understand why. Again, the structure is localized. That's what we want to say. Grain size in new alloy is smaller, and random texture, actually, which is better than columnar grains, is not preferred. And then less geometrically necessary dislocation density, in the material. And these actually contribute from the eutectic acetic cracking. That's why I'm asking you in the carbide cracking. That time we haven't identified very much, but no metallurgical phase as well in this new alloy system compared without aging. But the CM247 is a lot of problematic at length scale that we're talking about yesterday. You find some liquation, liquid film, carbide, gamma prime eutectic in the unaged sample. And this first generation here, once heat treated, you can actually recover back the gamma prime certificate, and carbide has been observed after heat treatment of this new alloy here. We use a atom probe to really map the composition in 3D, what happened. So there's isosurface of carbon, chromium, and aluminum atom itself in this one. So it starts to form gamma prime, and this is what the gamma prime that I show you is not defect. This is a gamma prime after heat treatment, actually. So you will see not only primary gamma prime, you see a secondary as well. But anyway, this needs to get the right heat treatment protocol to basically homogenize the structure later. But I leave that for other talk. It's not for this one. But anyway, if you see the property of these two new generation as printed and heat treated, then you will see it's involved a lot of testing you will see that as printed condition, the strength of this can be recovered by heat treatment. I mean, at the as you know, this is anomaly. The stress here is this is the typical shape of nickel-based superalloy stress at high temperature, but yeah, it's recovered back due to the gamma prime precipitation. And this actually map back to the very first slide. That strength and creep property of this has been improved by, I mean, is quite close to CM247 in AM, but still not very matched to the 718 yet. But I please note this point. I will talk to you a little bit more. This is 0.2% proof stress of the first generation alloy. And this is what is it here in terms of creep life. It's actually better than CM247. So, but it's performed about the same temperature capability. But this one also not print easy as well. I mean 718, because this is a gamma double prime strengthening material. And in terms of the second generation, we do the same. And you will see the green line here. At 900 is printable and is actually performed better than the first generation series that you can see without crack, the same. And the second generation also no crack and with improved property. So the performance of the material go up to 900 centigrade. And then we also doing hardness and distortion for this new material as well. So hardness with as heat treated and as printed, you will see the hardness is covered back compare against several material here. So we in second generation we also have several series of the material, and then we also do the bridges structure to characterize the distortion in as fabricated or as printed condition for the number of alloy, and you will see that the new alloy actually has minimum distortion compared with other two. Like CM247 is open up significantly 5 millimeter here, and then increment 718, for example. So we then now need to think another factor, as I mentioned earlier as well, because if this AM actually apply to the thin wall structure, the property will be different again. So that is so many factors we need to consider. The effect of material, if there is no side effect, it will be like this. But if no side effect, will be strength will be uniform, right? But with the side effect, the wall thickness is actually affect your property. Again, you need to take this into the alloy design consideration. Yeah, with the thick section here, if you want to print this part, this is the kind of part of something, I think bicycle or something like that. Again, you will get the very low surface to volume ratio and AM surface finish. In this case, we assume not relevant at this stage. So we characterize in terms of the side effect. I mean, this data is size-4, but we also do for a particular application. We didn't show it here, but you will see smaller, you get very low strength and ductility. With the larger, you get better strength, but again, you can customize your your property based on the size, and this is really important information to consider in mechanical simulation and also design for the application that you are looking at. So basically, just want to summarize here. So development of alloy is just because we want to develop a new composition that get the manufacturability that can be processable with the increased operation in temperature and decrease in crack density. And you will see that the performance of increment 718 is not actually ideal anymore. So we need to find a better material that sits here with additive manufacturability and also reduce crack susceptibility as well. So the performance at the temperature, at this critical temperature here, give rise to the different generation. I think now we have 4 or 5 alloy company, I mean, with the new generation of high temperature application. And with that, I think this is just I want to mention something that this is not relevant for nickel, but just to show that the impact of this definitely all directly will be powder feedstock company, right? Which there are a lot of companies doing on that in Germany, in UK, in USA. And then we also influence this one for a number of applications like energy, nuclear, and this is definitely all high temperature 3D printed part that are available now, even in SpaceX, X1, GE, NASA. So with that, just want to summarize the talk. This alloy by design approach is not rely upon not only empirical development of the bucket chemistry or statistical model. It had to use compositionally isolate high-performance engineered alloy specifically for additive manufacturing. And alloy composition affect the melt pool geometry, as you see before, subsequent grain structure, and suggesting that different processability are required for different alloy. The AM microstructure localized depend on the process condition used and thermophysical property. Effect of composition on processing microstructure can be predicted using compositional tool on the right length scale. Again, the length scale is important. Solid solution of the new additive manufacturing alloy has been observed in the as-printed condition with no secondary phase gamma prime. But after homogenization, we recover back the strength of the material. And then this AM process informed alloy by design approach exhibits a good balance of design of critical property, resulting in crack-free, high-strength, printable superalloy. So that is the ideal things we want. But again, we need to add another bit with targeted application as well. That is the key. So with that, I think thank you very much. Just not because all this presentation finished, but for the whole course for us today, for this week as well. Thank you very much. Just want to ask you have any question before we, I think it's probably 10 minutes, right? 10 something, 10, 15 minutes.
Sir, can you go back to the size effect slide?
Which slide?
Size effect. Strength as next.
Yeah.
Yes, sir. Yeah. So, what is the reason for reduction in the strength? You said size effect. Is it because of the variation in the microstructure, or?
Yes. I think I have a slide yesterday showing the columnar grains and the trap of some feature in the microstructure. The smaller, I think this is for yesterday, that I have a diagram showing that, and that affect into the property.
Okay, so can we enhance it by doing post-treatment?
That is something we haven't. I think in this one is titanium 6-4. There is a dedicated paper for this one. I think I can't remember that. This is not my work anyway. It's my colleague. So you may looking at that. But this is Thai 6-4. That means after post-treatment, even that is columnar grain ply beta. Yeah, it is. I have to say it's different from nickel-based superalloy structure. So I'm not sure. Probably yes. Probably yes. Probably yes. Yeah. But they do both as fabricated and as heat treated. That paper is probably in Acta Biomaterial, or by material and design, something like that. Yeah. Back in 2014, 15 as well. So 10 years ago. Yeah. I think, but on top of my head, probably a little bit, not a lot. It doesn't, yeah. But again, that is based on Thai 6-4. It's not nickel-based superalloy. If you want, you can design for nickel-based superalloy. But because why we can do this kind of small testing like this, at University of Oxford, they have the ETMT. Yeah, electrical thermomechanical testing, right? Yeah. So they can deal with the miniature tensile test pieces.
Micro tensile.
Yeah. No, ETMT. I think electrical thermomechanical. Yeah. If I may be wrong, but yeah. But it's the abbreviation ETMT. You can use digital correlation, DIC camera, to look at the strain development during testing as well. That's what they operate on the machine as well. Yeah. You can go back to the paper. I think the first author is Dr. Enrique Arabord. Yeah, he is a co-founder of the company as well. I'm not. Any other question? Yes, sure.
Yeah, Professor, thank you very much for a wonderful presentation. It's very insightful and inspiring also to look at this. I just have a few questions. This regarding the length scale you are emphasizing on the 1 mm, and
Okay.
then you translated it to the macro scale. I could not get it. So
It's another way around, from micro to macro. Yeah.
right.
We upscale.
So you were saying 6 orders of magnitude you were upscaling.
Yeah, from 10 to power minus 6 to 10 to 2 millimeter scale. So I'm talking about component scale.
Component scale. So it's 3 to 4 orders, right? Because 10 power minus 6 meter to you are going up to 1 mm. Because you were doing it 1 mm.
But that our target is to target something 0 centimeter scale.
Okay.
So 10 centimeter, again, you can say it's 4 or 5, yeah.
Yeah, so your intention was to do the micro scale molding at 1 mm length scale so
Yes.
that the output can be easily translated at the macro scale, because your element size is 1 mm even in the macro scale model. Is it what you are telling?
The element size in the macro scale is 1 millimeter.
1 millimeter. So even at the micro scale level also you were taking
1
the
millimeter.
length scale up to 1 mm so that the output parameters can be easily translated into this.
That is the idea.
That's what.
But 1 mm in melt pool, if you one by one, you will have to scan probably 100 or 50 layer, which is impossible in the melt pool simulation as well.
Right, right.
So there will need to be some way. but you're right. In terms of length, we try to capture 1 mm.
Okay.
And that you see a lot of paper. It's not just my paper.
Right, right.
A lot of paper looking at that and try to find some way to link this information across scale. Yeah.
Yeah. Got it.
Thank you. Yeah.
Actually, so when we talk about the part scale model, but during the part scale model, typically we have, we generally simulate just a layer in context of making a cubical sample or like that, right? But the geometry of the part itself, when it becomes complicated,
Yes.
there are down facing surface, there are up facing surface, there are curvatures, everything. So those geometrical effects, in order to incorporate those geometrical effects into the macro scale model, is it possible right now, or it's because those
that is the criticism for funder. Everything, what the AM5 is used in the real application. But I think, as I said, it's about the application that you identify. If this part is for small part, it's not big part, but complicated shape, that I think that is a targeted application we look at.
yes, because
So that means it's not going to be a bulky, it has to be delicate
because
component,
if
right?
if the modeling, it's a macro scale model is in context of simple cubical samples. If we prepare the micro scale model, I can trust that it might be giving some correct result. But there are companies who are for complicated shape itself, they are developing the part scale model.
Yes.
And they are claiming that the stresses and are comparable to the actual building, means what the stresses we
But
also
first,
building.
I have to point to say, First is actually, again, the part that you're looking at not going to be bulky or simple shape. It has to be delicate part. Second is about statistic. So AM is statistical. I mean, the statistical data from modeling from experiment will be used, I mean, incorporate with the macro global model from mechanical field. So if we assume that, assume again, the stress is universal across this geometry. So we may use that state in this one to tell something. If you know the mechanical field of that part, I'm not sure, again, this is something probably thermomechanical people, mechanical engineer has to find a way to homogenize this way to scale this up to mechanical field that you say. Yeah. But I mean, otherwise, I don't see the way out for this one. So we cannot actually measure every single condition for that, right? For sure. But we need to find a way more representative to what you just mentioned. And then I hope there would be some success case or some example that we can use to prove this concept. But so far, I haven't seen it as
But
well to link.
there are companies that claim that software is able to measure for complex component as well the mechanical fields they can measure.
Everyone can claim, yeah.
But
I don't know. They may want you to buy their product, I think. Any other question? Yeah. Yes, sure.
I mean, relating with your yesterday's lecture on the solute trapping. So,
Okay.
what is the exact cause of this not formation of gamma prime in the ABD alloy? Though the thermal signature is reaching the solver's temperature multiple times, you don't see formation of gamma prime. Is really
I
surprising.
think from the solute transport or solute trapping and the microsegregation study that we do, we understand that there are few factors that new alloy don't have, because the way that ABD algorithm here select the alloy, they screen out the highly segregated element like hafnium, carbon, and whatsoever I showed you yesterday.
Titanium, aluminum.
So that I'm not sure it's coincident or not, but it seems that they don't select this for the new alloy composition, or probably with cost as well. And that's why you get in the segregation profile, you get the homogenized kind of uniform or average segregation profile. There is no preferred segregation or selective segregation. So that's what we found from that work. But CM247 LC or Incal 718, they have preferred. As you know, you evident a lot.
Yeah, we have also done that. There is preferred segregation. There is formation of gamma double prime also in the as printed state.
Yes. You mean
in the as printed state?
Yeah.
There is
which material?
IN 718.
Yeah, of course. We see it from casting, from additive. We seen that. Yes.
But it's a total surprise that you don't see the formation of gamma
Yeah,
prime.
that's because our justification from that paper, NatureCom paper yesterday, that we don't have kind of harmful element for that segregation transport. Yeah.
during heat treatment time you are preferring to have the gamma prime segregated during heat treatment.
Yeah, that's what I said. We call it print soft, and then we recover the strength later or harden later.
At the time of printing, it is
Solid solution.
It can cause crackings and all, but later
No.
on, at the time of printing, if gamma prime is precipitated, it can cause cracking, right?
At the time of,
At the time of printing means when we are printing the samples.
if it's solid solution, probably less likely.
Okay. Yes.
But
It,
if it has some non-equilibrium big or segregation or solute profile, that may cause some impact. Because just a short period of time, you can actually generate how to say, a big residual stress because the elements segregated to the boundary, and this may cause the cracking. Because as you know, you're not printing only one layer, you're printing several of thousand layers. Some layer below that may be already, we call intrinsic heat treatment. It's heat treated somehow already. So that's why at some point you will get some effective ductility dip due to that underneath thermal cycle. So that's why below that. But what we see is that the segregation here actually stop it. The crack is, I mean, I'm talking about yesterday talk, it stopped at the solute trapping zone. So that means there will be, that's why we hypothesize this may be some role into to stop or eliminate the crack. That's how we try to hypothesize. And that's why in the new alloy system, this segregation is actually not concentrated, but it's uniformly, but we call solid solution, right? It's solid solution in the material. So that's why there is no preferred segregation in as printed in soft condition.
There no preferred segregation, or there is no segregation? Everything is there in the solid solution.
I would say minimum, just for the sake of science here. Possibility is low. Okay, I think we probably call it, and then thank you very much. I will be here anyway until the end of the course here. Thank you. And next will be Professor Kumar for his talk. Thank you very much. Oh, it's used. Take away.
After break.
Couple of announcements. One thing is regarding the feedback form, which we are going to circulate now. Yeah, that is a mandatory. The feedback, giving a feedback form is mandatory for getting the certificate. So kindly fill the feedback form. That is one thing. And another one is participants who stayed in Dasa hostel. Okay. So we are going to send a QR code. So kindly transfer the money to that. You do the digital payment to that QR code. We are going to put it in the group. The people who stayed in Dasa hostel only. I am again repeating, the people who stayed in the Dasa hostel.
10th theory last lecture. So this talk will be on medical case studies of additive manufacturing. So if you see the outline of my presentation, so we'll quickly see how we can create an interface medical engineering application with additive. Quickly we'll see how we can say integrate additive manufacturing technology with the medical field. And as we know that additive, we need a digital data. So digital data in medicine, so now thanks to the computers, so you have CT, MRI data. So the medical image processing, now it is digital. So where that is the start point of your medical application of additive manufacturing. So you have either a CT data or a MRI data or ultrasound data or a PET, any scanning modality. So you have a DICOM is the one neutral file. So you can get these medical images in a DICOM form. So then that DICOM images will be imported to any one of the medical image processing softwares. So in my talk, We have used a software Mimix, Materialize, that is the software. So you can use any medical image processing software to convert your DICOM images. Further, you can segregate your tissues from whole bunch of tissues. You may be interested at a particular point of time, maybe bone, you may not be interested with the soft tissue. Then you can segregate your the area of interest as well as the tissue of interest. So then we are going to use a medical image processing for that. And once you have done that medical image processing of the images, so then we can save there itself as STL file. So basically we need to have an STL file to 3D print it or to additively manufacture your model. In this case is a bio model, which it has been acquired from the patient data. And then though you have say virtual images, but still why we need to have a physical model in medicine? Not only in medicine, even in engineering also, if we have a prototype or a model in a physical form, obviously it will give a touch and feel. That is much important in biomedical applications. A surgeon wants to operate on a particular patient, so the physical models are very much important here. We'll try to see what is the role of physical models in medical applications. And material is very important as far as medical application is concerned. So we have been discussing several materials which can be additively manufactured, right? But we cannot use all the additively manufactured materials for biomedical applications. We have a stringent requirements, something like biocompatibility, right? So then when can you say a material is bio-qualified, right? So then we'll try to see biomaterials that can additively manufactured. We have two things here. So if you have 100 materials, among the 100 materials, you may able to manufacture through additive maybe some 50 materials, for example. I may be exaggerated. Among the 50 materials, maybe a five or six number of materials may be qualified for bio applications. Means you must have some stringent requirements. Not all the engineering materials are qualified for the bio applications. So among the qualified biomaterials, then another constraint is that should be additively manufactured. You are talking about you want to create an interface with the additive manufacturing and medical applications. So we'll try to see the biomaterials that can be additively manufactured. And then, yeah, we have been discussing 7 AM techniques. But each AM technique, it will have its own unique capability. So then, how do you see in the medical perspective of these AM processes and application wise? I'm going to touch up that also. And finally, how do you develop a medical application taking a CT data to develop a device or a implant or a prosthesis or maybe a support device like a guide, or even it could be say for surgical usage, pre-planning the surgery or rehearsal the surgery. So how do you see that printed model? So how do you make use of that? Then how do you develop such kind of medical applications? We'll try to see. And finally, we have collaborated with couple of hospitals in Hyderabad as well in Nellore. So I'm going to share our experience working on these cases, medical cases, using additive manufacturing as a model or an implant or a prosthesis or maybe device. And then what could be the future of this medical additive manufacturing? That is none other than organ printing. What is organ printing? So again, organ printing, if you talk about, then what could be the material that you are going to print it, right? So majority of the time, your material is synthetic, man-made material. But in case of organ printing, the living cells of the own patient is going to become a material that you are going to print it, right? So that is going to be the future in medical application is concerned. I will try to give the state of art in the direction of organ printing. So that is what I planned. Maybe another 1 hour or 1 hour 15 minutes. Probably 1 hour I will restrict. Why? Because you have some other plans anyway. So this is the typical medical AM process, right? So it should start with a CT or a MRI scan data. So basically CT or MRI scan data is a grayscale images. So it is a grayscale image where you have a different contrast and different brightness, right? Say, and if you take a skull, for example, you take the skull, you want to scan it, typically it may be 500 or 600 slices, again depends on the slice thickness that you are setting it in a CT scanner. So typically you have some 300 or 400 slice of data with the skull that it has been acquired from the patient. And if you take the skull, so skull is a bone, and if you see inside the skull, you have a brain, that is a soft tissue, and you have cerebrospinal fluid, so that is a body fluid. So, but you may be targeting only skull, you don't want to get the brain information, for example. So in that case, we need to have a medical image processing software which can segregate which tissue of interest or region of interest you are looking at. So then you segregate that region of interest or the tissue of interest, and you reconstruct them. Why? Because basically it is a two-dimensional images. So then your 3D printer or additive manufacturing machine, it requires a three-dimensional STL probably. So the STL file, so which we can reconstruct from the two-dimensional images to three-dimension and reconstruct it as STL format. Now your journey is smooth now. Once you have a STL file, let it be a skull model, let it be an aero engine, your machine won't care what could be the geometry, right? So, and human anatomy is supposed to be the complex geometry. That's where this guy is winner. Additive is a winner where you have a much complex structures. Of course, human anatomy supposed to be the highest complexity, right? You have a lot of neurovascularity inside your body, right? And once you reconstruct an STL file, and then depending on the facility you have, you may have extrusion based AM machine or powder bed or DED or material jetting or binder jetting or VAT system, or it may be a sheet lamination, whichever among 7 processes you have, and it follows the cycle of that. So means taking a powder, and then in the yesterday also we have seen how a powder bed laser based machine works, right? So, or even it could be FDM based. So then once you make layer by layer, then now how do you see that model? How do you see that printed anatomy that it has been captured from the patient, right? So then how do you see, means you can use in several applications. We'll try to see some of them from the literature as well as with our experience with the surgeons that I'm going to share with you. So if you try to see the applications industry wise, so consumer products and electronics, that is 21.8%. That is the biggest share, and followed by motor vehicle, that is automobile and automotive together, 18.6. And it is almost on par with your automotive and automobile application. Your medical is sitting at the 3rd place. Medical and dental together 16.4. This is the Holler's statistic report. So one can not ignore the medical application of additive manufacturing. And you try to put it in a Gartner cycle. So that is expectations versus time. So you can see right from the technology trigger to the plateau of productivity. So as we know that this journey was started with prototyping. That's what you used to call this technology, the rapid prototyping. The prototyping applications, almost it is touching to the productivity stage, followed by non-critical aerospace applications, and coming to medical, orthopedicians or early users of this technology. The reason is simple. Orthopedicians, they work hardly on the bones or the joints, right? And then you have a jewelry applications, domestic home applications, and dental. Dental in terms of dental crowns, dental implants, right? Dental bridges. So you have several applications of dental, and then critical aerospace applications, architecture, sports, education and bioprinting. This is quite interesting, organ printing or bioprinting or regenerative medicine, whatever you call. It's coming in a big way, but we have to wait a lot, maybe 20, 25 years, maybe. Why? Because it's at the very beginning stage. So medical research and clothing, 3D printed clothes is coming in a big way. And construction industry, the additive is coming in a big way. Military electronics is another area where you can see, right? So then one cannot ignore the medical application of additive manufacturing from the statistics. So then the journey starts with medical imaging data. If you try to see this, the medical scanning modalities, it was started with the X-ray, but the problem with the X-ray, it is analogous film, one cross section at a time you are going to take, right? Basically that is a analog data, but now you have a computers, you have a computed tomography or magnetic resonance imaging called MRI. So your journey starts with either a CT or a MRI data that has been captured from the patient, and now you have these two-dimensional cross-sectional grayscale images. Now we have discussed, you have a software or which is a tool can process these images. Again, if you try to see a COVID patient, so a chest CT has been taken. So at this point of time for the COVID patient, so you may be much worried about the lungs, how much infection that the lungs, right? So in that case, you may not be bothered right now at this point of time, the ribs or the spine. So you are going to segregate the lungs, that is soft tissue, with respect to other surrounding tissues, right? So then you can adopt any medical image processing tool for that. So then you reconstruct which organ of interest. In this case, the organ of interest is lungs. So then you can segregate and save it as STL file and give it to the 3D printer and get the model. And then you can back and forth, say transfer your data to the CAD system or to the medical image processing, vice versa. Why? Because we need to design a customized implant. So AM is meant for customization, personalization. That is very much needed for the medical application. Each person is unique in his anatomy, right? And over the years, you put up the age and your body will get deteriorated, right? So, but you can exactly replicate or you can exactly mimic the anatomy of the patient, and then you may be taking this data, medical data, to the CAD software or vice versa. So then you can import this data to the CAD, or from the CAD to the medical you can do, and simulation. So you design one implant, say you have a femoral joint here. So you have a pelvic joint and you have femur bone here, and this is joint here. So somebody has met with an accident or some kind of trauma, so he broke his joint, for example, and then you are trying to design a customized implant here. You have designed by scanning the patient data, and then you have designed, and before printing it or before he or she going to operate, then we need to check the fitment of this joint, right? So then you can do a lot of simulation in this kind of tools, and 3D computer models. So we need to take it this data into 3D, or you have designed some joint or implant where we need to test against the maximum load conditions. So maybe you have a femur bone or a tibia bone. So obviously we need to go with the FEA analysis. But like if you take a neurosurgeon or a say a cardiac, so they want to study the blood flow or the fluid flow, then you can take this data into a CFD analysis, vice versa, right? So then depends, like whether it is structural analysis or a fluid flow analysis, depending upon the medical application that you are working, so you can do that. And then you need to make a physical model. Like you can see there is a tumor here for the patient. So you can print this model along with the tumor and the skull bone, and you give this model to the surgeon, and he can rehearsal the surgery exactly where is the tumor position and how he can resect. And while doing the real operation, so he can follow the same procedure. Basically, he is going to say optimize or reducing the operating time and increasing the precision. That's what it's going to give. Your additive manufactured biomodels that you are going to get it. So it will enhance the, say, the safety as well as the operating time has been reduced, right? So in that way, so then you can make a physical model also, then supply to the surgeon. Or for design validations, you do some kind of implant, so do the design validation for that. So you try to see some tools available in medical image processing software, like Mimics is one of the medical image processing software, and Simpleware another one. But both of them are proprietary softwares. But if you are looking for a open source software, this is 3D Slicer. It's a free of cost. So it will almost have the features which a proprietary or a commercial software will have. Basic tools like importing the DICOM images and applying thresholding and region grow and say saving as a STL file. So all that stuff can be done with the open source software like a 3D Slicer. Yeah, then you have a lot of virtual models. Then why we need to have a physical model, which it has been, say, acquired data from the patient, then why you want to print it, right? So why you want to print it, like say, your surgeon's confidence levels will be high. Why? Because if you printed this model, for example, you take this is a reconstruction surgery, maxillofacial reconstructive surgery. So in this case, so this patient who needs this kind of an implant here at the zygomatic arch as well as this orbital rim. So where your eyeball will be sitting here in this orbital rim position. So means at least your ophthalmologist must be involved in this surgery, and oral maxillofacial, and of course a neurosurgeon can also be the part of this surgery, right? But you have a multi professional specialized people here and patient as well. So you can have this kind of a model. They can plan very well. They can design the implant, and you can educate the patient once you have a physical model with you, and you should not get panicked, the patient, right? So then you can very well educate before he operates, he or she going to operate, right? And then you have a better communication between the surgical teams, and you have a good education to the patient, and it also assists the surgeons to diagnose and surgical planning. So before goes into operation theater, say he can plan very well, right? What kind of say tools or what kind of instruments or what kind of device he has to carry, he or she, right? And he can plan very well, and sometimes just for diagnosing purpose. Maybe that's the first level of application of any medical AM printed model, just for the diagnosing the, maybe, depends. Or even we need to do a rehearsal of the surgery on this model. So he or she should not do on the patient in the real time. So they can do a lot of rehearsal, and they can do a lot of simulation, or they can come out with the best or the optimal surgical procedure, which it may not be there before. So that is possible. Why? Because it can give you an innovative surgical procedure. Why? Because each patient is unique, and the reasons may be different. So as an engineer, we can standardize, like you follow ASTM, ISO for a particular kind of a test procedure. But that is not the case for the surgeons. Why? Because the reasons will be several. They cannot standardize, saying that if this is a surgery, yes, I can. No, that is not the case. Each case is unique, right? But anyway, so they can come out with an innovative surgical procedure once you have these kind of models with them. And you can create a customized prosthesis. So somebody had some, say 1 ear or one eye has gone. So you can take scan of it, and you can very well customize any prosthesis for that matter. And not only prosthesis, you can even place these implants accurately. So you have this implant, so you can accurately place without misplacing your eyeball into the orbital rim. Why? Because this is affecting your orbital rim as well as the zygomatic arch. So you can very well place intact these implants once you have a model with you. And then how do you get manufactured? Again, we have been discussing the limitations of the additive manufacture, the subtractive versus additive. So additive is very good without a additional cost, means which we discussed in the first lecture also. It's a free of cost. Complexity is a free of cost, right? So that's what where all these complex geometries, you have a lot of undercuts, voids, say internal geometries like neurovascular, any bio anatomy, right? So which is a patient anatomy. So it's very complex, right? It's very difficult to do a conventional traditional manufacturing method, but without any additional cost. So you could able to do this. And coming to materials, yes, we discussed, I don't want to repeat this slide, we have discussed in the first lecture also. And you have, AM processes, we have been discussing for the past 4 days. Yeah, you have several materials. Let me focus on the biomaterials, right? So why, how do you define this biomaterial? So what is a biomaterial? So biomaterial, if you see the definition, this is the synthetic material or a man-made material. So that is used to replace or restore a function to a body tissue. It may be a continuously or intermediately in contact with the body fluid. So that's what where it will become very tough. Not all engineering materials are qualified. Why? Because it may be continuously or intermediately in contact with the body fluid. So and then so you are trying to replace or restore a particular function of a particular say body part or tissue, whatever it is. So and first and foremost, it should be a biocompatible material. What is a biocompatible material or biocompatibility? It should not elicit any kind of adverse responses from the body or vice versa. Once you put it inside the body, that kind of biomaterial, so it should not create any toxic environment in your body. So means it should not, it should be a non-toxic and it should be non-carcinogenic. Means it should not create any say cancerous kind of thing inside your body, right? And also it should, because of these stringent requirements, majority of our engineering materials may not be qualified for the bio material. And not only these requirements, then you try to see the kind of physical and the mechanical properties that your biomaterial is going to. It is almost try to mimic, if it is a bone, it should behave like a bone, right? And like say wherever you are using it, you have a different requirements. If it is a joint, if it is a knee joint, you have a different requirements, right? And if you have a TMJ, that is this is also joint. You have a temporomandibular joint. There is a joint here, and you have a joint here, and you have a joint here. But all the joints are different requirements, right? So it may be a mechanical, say physical properties that you are looking at that should match or nearly match whatever the tissue or the body part you are targeting to replace, right? And then of course the manufacturability. It should be amicably available and it should be easily processed. That's what your additive is here, like you can easily process any complex structures. And you try to see some polymers. So you see the polymer group. So you have plenty of polymers, biopolymers. You have a polyethylene and you have a polypropylene, PET, you have a polyamides, PTFE, and you have polyesters, PVC, PMMA, silicons and hydrogels. And you try to see these materials where it can be implanted or where it can be placed. So because running short of time, I am not going in depth. So on seeing this image, one can understand. So the biopolymers can be used almost like say head to the toe. You have a different the parts where you can replace the respective say the organs or the tissues, right? So you have all these materials and metals, right? Metal and metal alloys. So you have right from the 316L steel, right? It's a biocompatible material, and titanium 64 is predominant, and you have other titanium alloy which is biocompatible and FDA has been approved. And you have cobalt chrome alloys, and you have a nickel titanium, and you have gold, and you have a silver, and you have platinum, and you have amalgams for dental restorations. All these metal or metal alloys, so that too almost everything you can 3D print it or additively manufacture it. So that's the thing where we need to find what kind of process we are going to use for processing these kind of materials. And talking about ceramics, so you have alumina, zirconia, calcium phosphate, bioactive glasses, porcelain, carbon. So you can very well do this kind of a thing. If you take a bone substitute, probably hydroxyapatite, right? HAP. So which calcium phosphate or hydroxyapatite, so which you can 3D print it now. And then composites, though you have a few composites, yes, it's possible to even process the composites for dental restorations or kind of dental cements, so you can have biocomposites also. Yeah, and then that is about the materials. So then what about the processes? So if you try to see the VAT, I'm not going to repeat the principle of VAT photopolymerization process. The idea here is, so we can make 100% see-through materials, epoxy resins, which we can see almost like transparent, 100% see-through. Why we need such kind of requirement of that material, right? Say for example, if you take, there is a tumor here, and there is an implant required here, and there is a nerve here, you try to see the traditional way of gathering the information. They will take an impression basically, right? But impression will give only the outer surface, but a nerve is inside the jawbone. No way you will get traditional impression technique to know about this bone, the nerve. If dentist doesn't know about that nerve, so he may damage that nerve. So then if you have this kind of process, like it could be, say, you can make more transparent material, even see-through material, so you can very well plan, right? That is the advantage of VAT-based system. And DLP also same, but it is a mask-based thing. So the VAT, it's only a point by point with the laser it's going to process, but here the DLP, it's basically a mask. Entire layer can be exposed once and it will get cured, right? It's very faster than the previous one, but again you can get a transparent material here also. And multiple material, like say if you see this splints, wrist splints, so the splint, you can see the outer one, it's a flexible material, but if you see where the bone part here, so then you have a rigid material. You have a combination of rigid, flexible, but you can do it in a single setup. Why? Because you have a multiple material, the jets here. So some of them are dedicated to flexible or elastic material, some of them are dedicated to a rigid, or it may be opaque, or it may be a transparent, right? Or combination, you can print it. Sorry, and FDM, yes. So FDM, you can almost like a bone kind of appearance here. Say a bone kind of appearance here with the ABS plastic basically. So, and it's nowadays it's everybody will have this kind of a printer with your lab. Why? Because the Scott Crump patents expired long back, and now this is very started duplicated people, and anyway. So you have a powder bed fusion with polymer, or even with the metal. You may be interested with the metal. Why? Because you are going to print some implant, maybe a dental implant, or maybe a knee, or maybe a knee braces, or maybe a femoral joint. So you may be interested with the powder bed, and that to titanium 6-4, maybe cobalt chrome or 316L, right? So then you can very well process here, right? And then multicolor, multi-material, yes, you have a binder jetting system, you can very well do that. And you have a very big sized anatomy. Yes, you can make use of a laminated object manufacturing system, so you can make a big sized, say, body parts. And then coming to how do you, say, develop a medical application here, right? So how do you develop a medical application? So, first of all, how do you capture the patient data? The patient data, sometimes a surgeon needs to know about the internal structure of the, say, brain or the skull, right? And sometimes, so you are trying to do some sort of, say, artificial limb. You are trying to make a prosthesis of hand or a leg, so on. So in that case, hand or leg, you are trying to scan the outer surface, you are trying to get the amputee's hand or a leg or whatever prosthesis that you are trying to, right? So in that case, you are trying to capture, or even in case of a dental dentures, you are trying to get the outer surface. So in that case, go with any 3D scanner that is Normally you use a 3D digitizer, 3D scanner, which can capture in terms of point clouds, and you fit those points like a triangle, in this case is STL, and you fit a surface or a solid. So your job is done, right? So basically you have only two kinds of situations. One situation is surgeon wants to understand the interior part of the body, then you may be asked to undergo a CT, MRI, or PET, or maybe a ultrasound, whatever it is. So you have a different scanning modalities. That is a one option. Otherwise, external surface or external body part, they're trying to capture it. Then you go with a kind of a 3D scanner or reverse engineering or 3D digitizing, whatever you call. So let it come from a CT, MRI, or it could be a point cloud data, which has come from any white light scanner or a blue light scanner or any 3D scanner for that matter, right? Like your CMM, normally what you do, it's more for free-form surfaces. So either it could be internal or external. You acquire the data. Once you acquire the data, now we have discussed, if it come from this route, you have a two-dimensional grayscale images, that is CT or MR images, and you have other hand as a point cloud data. You have either a probe or either a laser, but you are getting a point, you're getting millions of points which has been captured from the amputee's hand or the patient processes where you are trying to develop, right? So there's a point cloud data. So then you have either a reverse engineering or medical image processing software, just now we have discussed. So this, it can be registered your data, right? So the density of the bone or the density of the tissue, then you can segregate. So then you can ultimately you create a STL file or IGS or DFX or application, which application you are looking at. Right now we are talking about AM, so probably you can stop it there at the STL level, that is the triangular facet level. Just take the points and then you join it, right? Or otherwise your images, your DICOM images, you can make a triangular mesh, then you stop it there. But still you want to do some kind of designing in a say customized implant, then you may require to go with a CAD model, a surface model, or maybe a solid model. So in that case you adapt any kind of modeling technique or a freeform modeling, and finally your CAD data is ready, right? So then how do you see that, okay, you captured and you printed, then how do you, the application I'm talking about, either just simply a model to diagnose the patient condition, the health, that may be the primary level of application, or even it could be a kind of a tool like a jig or a fixture or a template, while operating a surgeon will have some kind of support. So that is possible, right? Or implant, it may be directly, it may be a permanent implant or it may be temporary implant, but it's going to be an implant, or it may be a scaffold for tissue engineering, right? Or even it could be a surgical planning simulation FEA model or a medical device. So you have plenty of applications. Once you reproduce your body part, basically, right? Then you can make use of any one of these applications. So in a summary, so you start, you try to see the cycle here, right? So the doctor, in fact, the patient is going to be the start point here, right? So the patient, maybe the doctor will give a medical indication, and the radiologist will come into picture, either a CT, if it's a bone structure, CT, soft, it may be MRI, or it may be blood circulation or cancer, maybe a PET, your radiologist will come into picture, right? And right after, your computer specialist or the CAD guy, or who is going to process these images and then use those and 3D reconstruct it, right? And then once you have done that, just now we have discussed, and then you have additive manufacturing machine, you print that model, right? And where your AM knowledge is going to play a major role here. And of course you sit with the surgeon, right? And helping him. Basically it's an interdisciplinary kind of research, right? You need to have a lot of collaboration with the doctor, surgeon, radiologist, right? So then you do that. Finally, again your doctor or a patient is going to be the end user, right? So where you started with the patient and end with the patient, right? So this is a typical process chain. So yeah, I don't want to repeat the first lecture slide. The intention, which we understood how we can generate a topology or a lattice-based design. So that is right from the scratch, or maybe scan data like which you are talking about CT or MRI, data, right? So you have AM, yes, it is very good for personalizing, customizing, or mimicking the bone, or could be any tissue for that matter, right? And you have a pediatric heart surgeon, for example, a month's baby or a day's baby should be getting operated. So how complex that surgery is going to be? But nowadays you have FDA, of course, like ICMR in India. So even India nowadays, we are even have a national additive manufacturing policy, so which was initiated by NCAM and MITI, that is Ministry of Information Technology, right? So even ICMR is looking after, why? Because FDA, yes, it is a US based regulator, but India also we have ICMR, right? But anyway, you have some regulator who is going to give a certification qualification, right? Something like your aerospace applications, yes, you have a FAA or Semilac in India, like you talk about defense, and Srinivas may be good in that, like he can share his experiences also with the Semilac, how they are working with the defense people, the scientists. And here even ICMR or even with the FDA, yes, you can get it certified, right? So whether you can make use of that software or material or process or the product, so you have a lot of protocol here, especially these two areas, aerospace, medical. Yes, we need to get the regulator approvals, certifications, right, qualifications. But anyway, yes, people are doing it in a fast track, right? And personalized medicine, this is quite interesting, right? In drug delivery, even in Ayurvedic medicine in India, so people are even, the dosages, you can customize or you can personalize to the patient. Majority of the time you may be taking underdosed or overdosed, but you can exactly personalize your medicine. That's going to be the, in fact, FDA has approved recently, the 3D printed pills have been approved by FDA recently, right? So you can see a lot of say breakthroughs maybe in this direction. It is not surprised to have, you are going to swallow a 3D printed pill very soon. And also orthopedic casts, again a lightweighted, maybe aerospace, maybe medical, you can correlate, right? So lightweighting, here also bone, you are trying to so you have a cork-tail bone and you have a spongy bone, right? Or cancellous bone, whatever you call, like a porous bone, cancellous bone. So you can very well mimic, and you can personalize. You have a diabetes, for example, and he needs to have a sole, that is a personalized sole. Yes, you can do it here very well. You can personalize, you can customize, you can make as per the exact patient requirement or diabetes requirement, the sole that you are going to print it. Yeah, you can see tons of case studies where your AM is going to play a major role, like in terms of removing a huge tumor, and you can match the complexion and you can match the texture, right? So you can very well do that. You can print it in silicon, right? But still, yeah, there should be a lot of development must happen in this direction. Yes, across the world, at least 2-3 companies, they are even trying to, even they are printed this kind of structures. But anyway, we are going to see very soon, this is going to be the much revolutionized. So even you try to see, yeah, dental prosthesis, like you can have dental crowns, dental bridges, and where your mass customization is going to play a major role, right? So, and country like India, we have a huge requirement of these, each teeth and each crown is different. And at least people are looking, say in India, at least I can say you have a millions of people are who requires this kind of solution. Even you try to see aligners, teeth aligners is another area where just nowadays you have, anyway, my next slide will talk about. So you can very well do a kind of a dental prosthesis or tooth aligners or hearing aids or hip prosthesis, right? And it could be a hearing aid or even it could be an AirPod. You have only 3 options, right? It may be L or XL or it may be M, but it can be your canal could be scanned and you can very well customize, personalize your AirPod, or even it could be a hearing aid, right? So you can very well do that. And try to see this kind of a teeth aligners. So like the early versions of these teeth aligners, normally it could be a kind of a clip or a kind of a wire kind of a thing, right? It looks very ugly. But now you can see like a LCD based system or a VAT based system, which you can print it in 100% transparent material. Hardly you can notice whether he or she won a kind of a teeth aligner like this. So even you can fix up an appointment, like nowadays you have 2C, right? So where they will come with the intraoral scanner. So they will scan your teeth, right? And then you need not move from your home. They will come to you, they will scan with the intraoral scanner, they will take that data, right? And they will make this kind of a aligner. That's the first sitting. And you can fix it. Maybe next sitting, maybe after 1 month, 4 weeks or 5 weeks, again they will come and get it. You fix up with an appointment. You need not go to the even dentist, right? So your supply chain, you see, try to see the supply chain or the logistics involved here, right? It's very simplified, right? But anyway, and hardly you can notice whether he or she won a kind of a teeth aligner. So yeah, so you can see several cases like this, and also the prosthesis that we are talking about, an amputee hand or amputee leg. Very well you can scan the survived one and you can exactly replicate, taking a mirror image of the survived one to the amputee side, right? You can very well do that. And like for kids, this is a kind of a Rex. This Rex, if you see, traditionally they make this heavy and size is also not for that child. But you can very well customize, you can make more lightweighted Rex here. These Rex are lightweighted and personalized as for the user's requirement, right? And here also you can see a lot of dental aligners, and you can see these kind of and in India, like we have Jaipur, we are very good in doing this kind of prosthesis, right? But we never see the kind of artistry involved. Always you will be given one color, one design. But now if you could able to integrate your 3D scanning technology and 3D printing technology and matching the kind of profession you are doing it. Maybe you may be she is a pop singer and she is a software professional and he is an athletic, right? So you can very well, they can choose the color or the texture or whichever way, and a lot of robotics also involved here. But right, which we can even see a kind of technology which will enhance the better societal life, right? So anyway, so which we can see a bike rider, so where the process is hardly you can notice whether he or she won a kind of a prosthetic leg. Hardly you notice it. Like you can very well match the complexion or the textures, right? So where you can very well do that. And let me come to the last part of my presentation. Like say you try to see these cases. Our experience with this is the first case study I'm going to discuss is the cranial. This patient met with an accident, and this skull part of the cranial, the bone that which protects the brain, you will call that portion of the skull is a cranial bone. The cranial bone. So here the challenge is your bone is not uniform thickness across the entire skull, and then the challenge here, we need to design carefully and we need to take several measurements and we need to do a correct fitment of this implant against the skull. And you have a cerebrospinal fluid, that is a fluid which it generates in the brain and it will pass all the way to the spine. Right, and the fitment is very important here. So you can do model, simulate, and print it and test it, right? And then you can have. Sometimes we need to we need to simulate the number of fixation points. You are going to fix this implant against the skull of the patient, and then that fixation points location, your pressure of that cerebrospinal fluid will be varying. So what could be the optimal fixation position of these screws, and how many number of screws, right? So we can very well do a simulate such kind of a thing, and the material property also. Like then hardly you can have material which is biocompatible, and that too your facility must support such kind of material, right? That is another criteria which we need to understand. And finally, you designed, fabricated, but here you see it is a kind of a sandwich structure, your skull, right? So you have the inner thickness of the say skull is around 0.8, 0.9, and outer is 0.4, 0.5, and in between you have a porous structure. So no other way, other than 3D printing, you can make in a single setup, right? So it is impossible, right? But here and that it is a patient specific. So you can very well adjust this porosity as for the patient requirement, the personalized implant which you can design, right? And the next case study is a dental case study. So as I already said, like you have this kind of a nerve here, and through a conventional method, they will take an impression. Taking an impression, you will get only the outer surface of the jaw information, but not the inner, the nerve, alveolar inferior nerve. And ultimately, they are going to fix this screw, and by chance they may under drill or over drill, right? So then, if you have a model like this, so this we have done almost 12, 13 years old case, this one. But now you have a see-through material, right? Like you have a LCD based or a SLA technology, which you can even see through that, say the nerve which it may be passing from this condyle portion and touching mental foramen, and again it will come other side of the condyle portion. So you can very well give these models and sit with them and then let them rehearsal the surgery, like what could be the diameter of the drill, right? Pilot drill and all that they can do on this, and what could be the orientation, what could be the depth, right? And what could be the diameter. So all that they can rehearsal or they can plan, and straight away they can go to the operation theater and they can fix during the surgery, right? This is where we can make use of this. And another case study, it's a mandibular distraction osteogenesis. By birth, she had asymmetry, or the bone is not grown proportionately. That's what you can see, the left side and the right side. And because of that, she could not open. Normal opening is 5 to 6 centimeters, right? And then here, and bone will have its natural growth, and that depends on the age, gender, the family, and then other habits, food habits and all. But anyway, so here in this case, the CT data has been taken and it has been reconstructed. Now this is a mimics generated 3D model after taking the CT data and reconstructing it. And then they will use this device called a distractor. So they will cut the bone and they will leave that bone, and bone will have its natural growth, right? And then that growth, that will be controlled by this device, and if you rotate it, it will be advancing, right? And then ultimately what we need to do, if you try to see, this is a biomodel which it has been taken from the patient scan data and it got printed, which you can see if it is semicircular, the healthy patient should be a semicircular one, but because she had a deformity or by birth the bone has not grown proportionately, which you can see, we can assume that this is the healthier side, the ramus height is this much, and you have the ramus side, other one is very shorter. We need to lengthen this bone and in such a way that it should increase the length up to this, right? So and then we need to twist the bone. So all that we can, so it will vary from patient to patient, right? And for this, for her case, so we can do all that vector calculations. So what could be the twisting angle and how much we need to twist and how much we need to stretch that bone, right? So which you can see, this is before the surgery and after the surgery. But still we can notice some kind of, say, asymmetricity here. That you are correct. The reason here is, so the bone growth is there vigorously up to teenage, but she is 8-9 year old. Now it has been overcorrected right now. Once she turns 20 years, it should be, final correction should be done. And the next case study is a cancer patient. You can see this is a cancer affected bone. So then here what we need to do, we need to anyway we need to remove that cancer region, the bone, right? Then how much we need to remove, where we need to remove, and if we are going to remove that part and we are going to say supplement with some implant here, we are going to fix an implant here. So what is the size of that implant, right? So then we can do all that in a software, initially designing it, modeling it, so then taking the survived one as a assistance, and we can do mirror, right? And then you can make use of this model, cut it, right? So and then finally you can design optimal implant for this case. So in this case, again, we are taking the help of lattice structures. That's what we discussed in the previous discussion also. This lattice structures, again, it is patient specific, which we are trying to mimic it. And it will serve both the purposes. One is lightweighting, another one is osseointegrity and the cell growth, right? So then that will be taken care here. And they will use these plates, but this is our first attempt to fix the implant into the patient body, but we could not do it. There will be several procedural things. But at least what we have done in this case is we have given these models for them to do a kind of, say, the plates or the steel or the titanium plates, they bend like this, and they will take a fibula bone here. So you have two bones here, from the knee to the ankle, there will be two bones. One is tibia, that is a load carrying bone, and you have God has given one spare, that is a fibula. If anything goes wrong, the bone grafting, self grafting, they will make use of that bone, and they will make use of that bone, and with the help of this as a say support, right, or the guide, so they will try to say fix it or carve it during the surgery, and they are going to fix it like this. But that is going to not so a better solution. But that's what we came to know, that though they have done this is with the post-operative X-ray image, but it should be revisited, the surgery. Why? Because it's not a successful surgery. So the conventional, wherever you have a conventional surgeries are getting failed. So this guy is there to say help you out. So wherever you have a conventional procedures, surgical procedures, or making very tough or complex. And the next case study, this is a TMJ, that is temporomandibular joint ankylosis. So you have this joint here, lower jaw, upper jaw. This joint is responsible for articulation of your mouth. That is 5 to 6 centimeters for a healthy person. You must open 5 to 6 centimeters, opening of the mouth if you are healthy. So, but you can see she had a birth problem. The one side of the joint, you have two joints either side, right? And one side of the joint, it got fused by birth. But because of fusion, what is going to happen? If you have two joints or free, then articulation will be normal. But one side like this, and how she could able to open that she has been surviving for the past 20 years. And then, which you can see anyway, so with this is what I am talking about. This joint got fused, but if you see the other side of the joint, it is free. But again, God has given a hint. We can take these as a reference, as a healthy side, and we can design the same geometry, dimensions, form, everything on the other side, right? And first we need to do a distraction osteogenesis, as I already explained this procedure. We stretch forward this bone, right, which we can see 1 mm, 2 mm, 3 mm, 4 mm, 19 mm, 21 mm. So like this. So now we can see this is the initial condition before the distraction. Now we can see after distraction, now it has been aligned. Right? This is during the transformation, fixing that distractor during the transformation, and which is this is the before and this is the after. But still, the game is not over. Why? Because this should be why this is so complex. If you ask any oral maxillofacial surgeon, what could be the toughest surgery? If you ask him, immediately he will say TMJ ankylosis. Why? Because you have a lot of nerve system here, very adjacent to this joint. That's very challenging. And that too, you are trying to almost what you are trying to do. So you are going to resect that the fused joint, and freshly you are designing and you are fixing the implants over there. And this is what I am talking about. So anyway, this is CT data, and then designing, modeling it, and again taking the other side as a, and basically you have the upper jaw, that's called the maxilla. You have a mandibular mandible, right, from the lower jaw, that's called mandible. So what I am trying to say here, so you have a, we need to cut this portion, and you have this mandible condyle portion, and maxilla you have this zygomatic arch, and this is a joint, right? This is going to be a joint. We resected this, and this is what it's going to be, and then we are going to fix the screws here on the maxilla as well as in the mandible side. This is what it's going to be. This is a prototype, and this is the implant, which it has been printed in titanium 6/4 powder bed system. And anyway, these are the and we design a template also. Why? Because he or she, the surgeon, has to fix the drill a hole and fixing that screws, right? Just like that, he or she cannot drill, right? Say, and that it is a patient specific. So based on that, so this is the templates. They will get a standard templates also, but that won't work out, right? This is patient specific requirement. So then this is the template design, and with the help of that template, so they will use their say drills to fix that screw, right? This we filed a patent. This has been granted in June 7, 2024. This for the surgical procedure, the TMJ reconstruction. And I was evident inside the operation theater along with Ian Gibson. Probably this is the same Gian course which I conducted. Yeah, that is during his visit, and we conducted 2 courses. One is probably you might have read his book, Additive Manufacturing, very well-known book by Brent Stucker, Ian Gibson, and now you have one more author also. 3 author. First author is Ian Gibson. So we have a collaboration through that Gian only, first Gian and second Gian. So during that time we fixed this surgery, and we have and I was also there inside the operation theater. So it is very brutal kind of surgery, but anyway, so nevertheless, say for the past 20 years she has been surviving, but once it has been released, the joint, after 20 years, now this joint has been released, means now she could able to open her mouth 6 or 5 centimeters, right? So after 21 years, and this is during the surgery, this implants, which it has been fixed from the upper jaw, that's called maxilla, and the lower jaw mandible. This is mandible side, and this is the maxilla side. Now she doing good, and she got engaged recently. Oops, I'm trying to play the video, but anyway. Yeah, now you can see she could able to open her mouth, normal opening, 5 to 6 centimeters, normal biting, normal chewing. So after 21 years, she has been surviving like that. So there is no harm for the life, but the societal life, better societal life, right? So that's what this technology not only meant for, say, non-living things, but it can be meant for the living beings also, like where your conventional surgical procedures may not be help you out, but this technology is always you can integrate. And last case study I am going to discuss is basil osseo integrated implant. This is an accident case, and none other than this technology will give a solution for this. Why I am saying is, so he met with an accident, he lost his 5 teeth along with the bone support. If you have a bone support, they use a conventional implants 1-to-1. They will fix these screws, and they will fix the abutment, and they will use the artificial tooth. But unfortunately, she lost 5 tooth along with the bone. So 1-to-1 conventional, no way. So then indigenously we need to design implant. That's what design, and then this is a placement and testing it for the biting force, chewing force, and all that. And this is the prototype, and this printed on titanium 6/4, again on the metal powder bed system. Yeah, this is during the surgery. So this just snap fit here, right? This during the which we can see this implant has been fixed here. We published in Rapid Prototyping Journal this case. Yeah, you can see this is a post-operative surgery, this implant, and this is a permanent implant, and on top of it you have these at least 4 teeth has been accommodated, right? So in this way we can indigenous design of the implant. There is no other way to do a surgery here. The standard implants won't work out here. So you can see several cases where some abnormal growth of the tumor, or some cleft cases, or some say trauma cases or accident cases, you have plenty. And okay, so far we are discussing about the bone replacement, joint replacement, or some extent a simple tissue thing. But what is going to be the future? So future is going to be the organ printing, right? So where the material need not be a synthetic material, which is a man-made material. No, absolutely it is a natural material, and that too it may be a living cell is going to be your material that you are going to print it, right? And you make a bio ink. Normally it is a kind of injections kind of technology, like you have extrusion with a kind of a syringe, right? Then you can make this cell ink. You add some collagen, like a natural collagen, and prepare it, add some nutritions, right? And then do a cell cultivation, put it in an incubator and reactor, test it, and again you put back. So that is the idea, right? That is about organ printing, or say bioprinting, or regenerative medicine is all about. So they will extract a cell from your own body and put it in an incubator and add proteins, cultivate it, incubate it, test it in a reactor, and finally if it succeeds, then put back into the, they will take a piece of even the own organ, or maybe the living cell, that it may be stem cell. Now everybody is having stem cell bank now, so you can make use of those stem cells for that matter, right? So that's what, where then just try to see what is state of art. Yeah, you can classify these organs into a 3 or 4 level complexity. First level complexity, for example, skin. Yes, people have already done. Blood vessel, second level complexity, right? They have done it. Bladder, they have done it. But maybe 4th level complexity, like you target a complex organ like a liver. Liver may be 1 to 1.5 kg weight, and you have a huge mass over there. But maybe time may be the answer for that. Nobody dreamt that the other organs or the tissues can be implanted, right? But we have seen a lot of breakthroughs, right? So yeah, let me conclude my talk here. So what we discussed during this lecture, we started with medical imaging technologies, as a CT, MRI, how we can extract the data and how we can process the images and how we can reconstruct it and we can print it, and how do you make use of those printed models, maybe virtual model or diagnostic model, pre-planning models, customized implants or processes, through my case studies and through the literature also. So I have explained how various applications of your bio model or implant or device or template or anything for that matter, like which it has been extracted from the own patient anatomy, right? Yeah, and then finally organ printing. Yeah, I would like to acknowledge here, this is a collaborative work. So without the need or the requirement should come from the doctor or the patient, right? So we have a very good team, collaborators from Panniya Dental Science and Research Center, Hyderabad, Dr. Shekhar Reddy and Aditya Mohan, and we have Dr. P. Mahesh from Narayana Dental College for dental cases and for waddle maxillofacial cases, and then I have a couple of DST projects which I executed. And anyway, this we have already visited. So let me conclude here. If you have any questions, I'm happy to answer. Yes, please. Yeah, very good question actually. Yeah, that is the major challenge here. Yeah, that's what we tried to search with the procedure. What kind of a procedure for certification? See, yes, you approach machine vendor. Machine vendor says that yes, titanium 64 is a biocompatible, which FDA has approved. You can use it absolutely as a material. Yes, absolutely. It is certified, FDA certified. It's a biocompatible 64. Yes, you can make use of it. But challenge here is, so at the moment you process it, and you have a AM machine, and you are processing it, you are melting it, and you are doing some sort of autoclave and some sort of the kind of sterilization you are doing it. And again, we need to follow some guidelines for that FDA. But the challenge here is maybe why? Because we faced a lot initially, which we are first case which are trying to implant it. So yeah, in India still we are struggling, I can say. Why? Because not only in India, for that matter, even other countries also, they can say that it is got certified. Okay, material got certified, and what about the product at the moment you designed it? Yeah, still that is a challenge, but which we need to take some clearance from the ethical committee, and we need to do all this in presence of some committee. We need to do in presence of them. And ICMR, I think there is some regulatory kind of a policy matter, even with one of the institutes in Trivandrum, Sri Chitra. Yes, so then they got a kind of CMRI, and even not only FDA, even you have some kind of accredited bodies. That's what they are doing, Sri Chitra. So it has been accredited by some kind of say regulatory body, not exactly FDA. Yes, it is possible. Yeah, as far as FDA is concerned, they may say that it is certified material, titanium 64 or cobalt chrome or 316L. But at the moment you process it, you design it, you print it, and putting into the body, yeah, we need to follow that kind of a thing. That's what our experience. But still, I can say it should be foolproofed, but not happening in that way. Or otherwise, commercially, if you see that initially we printed from Israel, one case. Why? Because they have a certified, they are giving a certification along with the implant which you printed. We send the design, they print it. But still, it should be further. In India, I can say like some people are printing and fixing it, but it should be taken care like all these processes. Yes.
And are they coated?
No, it's not coated. It's only titanium 64. It's a printed as built.
So it is
and then
as printed. As printed, you have actually used it in the
yes,
humans.
after sterilization, autoclave, and some. Yeah, it's not coated. We can do a coating also, hydroxyapatite coating or any other coating.
Okay.
As it's possible, we can do it, but we didn't coat it.
Okay.
Correct.
And so what's the procedure you are adopting actually to incorporate into patient?
Yes, that's what. Actually, the dental, if you take this, the dental association, and they have some sort of committees, and then it has been approved, and then the surgery should be done in presence of them, that committee and the ethical clearances. Yeah, and otherwise one or two cases from the Israel we got certified. Yeah.
Of course, you take the patient's approval. And
Yeah, that's
concurrence.
always, we'll take a declaration from the patient that normally we'll take, and over and above, it should be taken.
And going forward, since you have completed the last 7-8 years before,
Right.
now are you following up with those patients and how that metal is behaving? With
Yeah, very good question. Yeah. Why? Because, yes, yeah, so far 7-8 years, and depends, like it is a permanent implant or a temporary implant. So what I discussed is a permanent implant. 7-8 years, it has been followed up. It's under observation.
I mean, how the material is behaving with the body response, that becomes a data bank actually for the
Correct. Yeah.
approvers.
Mm-hmm.
That's what I'm hearing in cases with stabler cups and other things. That the surgeons want to actually continuously take the data follow up with the patients, take the data, and give it for the authorities for regulation.
Yes, even with taking a population size like this and the age, and yeah, we can create even machine learning technique or kind of a AML can also be integrated. Yeah, that's good idea. Like, yeah, they have certainly some sort of population history, the data. So further, it can be integrated with kind of machine learning kind of thing. Yeah.
Small technical query I have. Small technical
please.
query. You are using Mimics software or
Mimic software.
Thematic?
Thematic, yeah, both. Mimics, and both are from Materialized Belgium.
Okay.
So Mimics is more like processing of the images,
Yeah.
and Thematic is for designing the implant.
I mean, so generally the important aspect of this design is to create the defect structure in the bone.
Yes.
Whether it is maxillocranial
Facial,
or
yeah, correct.
facial or is it acetabular cup, the bone is defective. There is some defect because of the cancerous cells and
Yes.
all. So the defect region has to be captured and redesigned, and the
Right.
positive part of that, the negative part of that defect
Yeah,
structure
it is
has to be
symmetric.
incorporated.
It is a symmetric defect, or the, yeah, then we will mirror it. But is a asymmetric, we need to do right from the scratch. If it is symmetric, yeah, it will be mirrored and it will be redesigned. Yeah.
Mostly what we see is an asymmetric structure only,
Yes.
kind of thing.
Correct.
That has to be incorporated into the implant. Then
Right.
So which software is most suitable, Mimics or Thematic for that?
Yeah, no, see, I don't want to comment. Normally these two, one is for processing, another one is for design. So without that thematic, you cannot design. Mimics is basically for basic.
Is there any open source software
Yes,
available
yes,
which
3D
can do it
slicer.
effectively?
3D slicer, I mentioned in my presentation.
Sorry to just extend. What I am hearing from other researchers in this aspect is they say the exact 3D slicer and all is not able to exactly join the
Correct.
defect regions.
Correct. And also that is not FDA approved.
Wh- wh-
Those softwares may not be FDA approved, but these commercial softwares are FDA approved.
Okay.
Yeah. Yeah, obviously, if you have a commercial system, then the capabilities and the features may be, and accuracy may be high versus the open source softwares. Correct. Yes. Yeah, actually, that is very much needed, open source softwares in this domain. Why? Because all the way it is very expensive. As far as design is concerned, then they need to bear the design charges, and the 3D printed is a titanium. Obviously, it is a costly material. Yes, it should be further. We filed Indian patent also, both way. That is around 25. No, not lakhs. Maybe 2.5 lakhs, not 25. 2.5. Stop it here. Maybe you can take the examination. The people. Yeah. May I ask to occupy one row the credit, the people who opted for the credit earning, which one? Can you please occupy this column? The people who opted for the credit. Yeah, and rest of the people. Yeah, you can occupy this column, but you sit at the end.
the faculty or the people who are not opted for the credit, but still you want to attempt the exam, you sit at the back.
S006, SG06, SG14, SG14, SG23, unique number SG23, SG25, this, SG26, SG36, SG36, SG41, SG39, SG43, SG43, SG47, SG48, SG48, SG49, SG56,
So, very good afternoon. So, I would like to invite you all for this valedictory function. One week Gian course on physics-based and data-driven modeling in additive manufacturing, conducted by Department of Mechanical Engineering from November 25 to 29 to 2024. And it's my privilege. We have very renowned expert in this area, the modeling and simulation of additive manufacturing. So we had 5-day deliberations. We are fortunate here. So Professor Chennapat from Queen Mary University, London, as an international faculty. So as we know that the aim of this workshop is to provide a comprehensive understanding of various aspects of physics-based and data-driven modeling in additive manufacturing, and to train the students, like we have PhD scholars as well as one UG and couple of PG students, and also we have good number of faculty and the R&D persons. So we have 3 scientists from DMRL and 2 industry people. And we discussed a lot and the state of art information on the additive manufacturing and inculcating the research interest in this additive manufacturing area. And totally we have 60 participants, and effective it was 54. So those 60 people are registered, but 54 people are turned up, the full attendance. The following content was delivered during 5 days. So there were 10 theory sessions, each one of 1.5 hours, that is totally 15 hours was conducted on fundamentals of mechanistic modeling, modeling and simulation of laser powder bed fusion, additive manufacturing for microstructure and mechanical properties, thermomechanical modeling of additive manufacturing to calculate residual stresses and distortion, and fundamentals of data-driven modeling and its application in additive manufacturing, multi-scale, multi-physics modeling of heterogeneous non-equilibrium microstructures in metal AM, design for additive manufacturing, basics of machine learning, integration of physics-informed machine learning and digital twin to additive manufacturing, and finally the lecture number 10 was on medical case studies of additive manufacturing. And we had 7 labs, which is from the prediction of composition change by machine learning techniques, design for additive manufacturing, that is lattice generation using N topology software, simulation for defect reduction and microstructure prediction using ANSYS Fluent software by the postdoc of Professor Chennapat, and build setup preparation for metal additive manufacturing using 3D Expert software, and finally working on metal additive manufacturing machine and post-processing techniques for metal additive manufacturing parts. And an examination was also conducted at the end of the program, that is today between say 12:45 to 1:15. We had an examination who opted for the credit earning. Around 18 people were opted and written, and we are going to evaluate them considering all the criteria, like right from the attendance and other factors. So by next week we are going to give you the grade once we complete the assessment. Probably you can expect by next week the grade sheet will be sent to you. And finally, I would like to thank all the participants to make this program a grand success. Without participants we cannot do anything, but I am very much thankful for the participants who came all the way, which is catering almost all parts of country. So thank you very much. And I would like to invite participants may I request to come and give your feedback. Kindly introduce yourself, where you are from, and may I request participants to come and give your feedback.
very good afternoon to all. So myself, Dr. Swaminathan. I am a faculty from PSG institutions, Coimbatore, Tamil Nadu. First of all, I would like to thank the coordinator for selecting me and my colleagues for attending this 5-day Gyan course. All the sessions were really informative, and we could able to know what is the cutting edge research that is going on in the field of additive manufacturing. So before attending this session, most of our research direction is towards the manufacturing aspect of additive manufacturing. So we never thought we can able to do this much amount of modeling which are possible in the area of additive manufacturing. So for throwing light on this particular area, I would like to thank the resource person. So all the sessions were really informative, sir. You throwed lot of heavy contents within a short span of time. The overall organization was also very good, and yeah, thank you.
Thank you, Professor Ravi Kumar. Thank you for letting me at the last moment. Actually, I was busy with my own stuff, so I thought I would not be able to make it over here. Actually, we did. Okay, sorry. So my name is Saurabh Tripathi, and I am a PhD scholar currently at IIT Kharagpur. And my supervisor, who is guiding my PhD, is Professor C.S. Kumar. So actually, during the event itself, I have reduced much of about it, but on the podium itself, I will thank Professor Ravi Kumar to get me into the course at the last moment, and I would like to thank Professor Chinnapat for all the questions, doubts, whatever I was having, solving it, means whatever queries I was having, resolving it. So a very kind thank you for letting me in and having some interaction with you guys. And I should appreciate that the campus is very beautiful. I did my masters from Jamshedpur, but compared to that, I feel that the Warangal is pretty much beautiful. Thank you very much. Thank you for the participation. Actually, I had a very nice interaction with a lot of participants over here. So this kind of event, apart from conferences and this workshops basically is a good place to interact with a lot of people who are working in a similar area. So thank you, Professor Ravi Kumar, Professor Chinnapat again for organizing this great event. Thank you.
Good afternoon, one and all. So I am Dr. Kedar Malik, professor in the Department of Mechanical Engineering, Vasireddi Venkataraja Institute of Technology. So I take a privilege to thank the coordinator, Professor Ravi Kumar Garu, and the resource person, Professor Chinnapat. And okay, the energy behind all these things, Mr. Kishore and his team also we should appreciate. We should not forget them. So I take this privilege to appreciate them also, because so we have been observing what the pain they have been taking to run the program successfully. So thank you, Mr. Kishore and all. After COVID, actually, we are observing that many courses are being conducted online. But even though if it is online, there are so many participants from long distances. Like we have participants from Jammu and Kashmir, also Jodhpur, Kharagpur, and so many people from IIT Madras, etc., etc. So that's a really great thing that we can see the national integrity here. So thank you very much. Thank you all. Thank you.
Good afternoon to all of you. I am V. Srinivas, scientist E from DMRL, DRDO, Hyderabad. So So first of all, my heartful thanks to Dr. Ravi Kumar for organizing such a important course on additive manufacturing, modeling and simulation of additive manufacturing. And also I heartfully thank Professor Chinnapat for coming from such a long distance and giving us a flavor of this modeling and simulation additive manufacturing. In fact, I have been looking for this course for last 1 year, to be honest with all of you. And I've been looking at different IITs, courses and NITs, if anybody would organize such a course on modeling and simulation additive manufacturing, because we know that there is not much expertise in this field in India, even at different places. So I've been eagerly looking for this course. And 4 months before, when I received a invitation from Dr. Ravi Kumar on this, I was literally jumping with joy. And immediately informed to our colleagues, and we three of us could make it for that reason, because this is a course which will give us some motivation and it will kindle interest in us to look for modeling and simulation, of which most of us are afraid of. We are good in our experiments and characterization, of course being a metallurgist, but we are little far away from modeling and simulation. So primarily this course with the able guidance of Professor Chinnapat, it kindled some interest in us now. We are going back with this enthusiasm that yes, we will also want to try our hands on modeling and simulation, especially, and we also could see that based on the work they have carried out, that a lot of work can be done, a lot of good output can be generated in terms of designing the new alloys, or in terms of improving the process control in LPBF, which are the real challenges right now, which industry and R&D centers are looking for. We want to really make parts which are repeatable and reliable, and which can also reduce the qualification certification aspects. And all these things can be minimized with the help of process modeling and simulation. There is a lot of potential in that. Though we may be in a very beginning stages right now, I could see the potential in this based on the experience of the professor. So I very much thank him for kindling such interest and enthusiasm in us, and I really wish that we should take forward this inspiration, not just stop at this point level. To be honest with you, I came with much more expectations of going in depth in this subject, but I understand that since this is an introductory course or an overview kind of course, yes, I request him to please plan an advanced level course where few specific topics are taken and we go in detail and depth in those courses. This course is like a broad overview of different aspects of modeling simulation. Some of the content we still need to digest it. We have to go back and revise it again and again to digest the content. So I am looking forward for advanced level course, much more deeper interaction, where we get into the actual modeling simulation and work out some solutions from that. Thank you once again for all the organizers and all the participants. It's nice interaction with many students, research scholars from IIT Jammu, IIT Kharagpur, and then different labs. Our RRCAT guys are there, and so it was very a good feeling. 5 days just passed like that here, interacting with all of you and with the professor. And I appreciate professor's patience also in answering our queries. We had several times interaction discussion with him. So thank you all very much.
Hello all, I am Sriram and I am doing my first semester PhD at IIT Madras. First of all, I would like to thank Professor Ravi Kumar sir for accepting the registration just 1 week before the program is about to start. So I really want to thank him at first, and second thing, I am really thankful to Professor Chinnapat sir. My research area is on the fatigue life prediction, and I think I wouldn't before attending session, all the thing which I have been known to do was about the experiments and structural level modeling like XFEM, maybe those kind of thing. And this is the first time and that I am seeing that computational material science modeling like the grain growth, crystal grain growth. So multi-scale modeling and multi-physics modeling at the various levels like microstructural, mesos level, and connecting those properties to a structural level. So like this is my first semester, so I think this course has been really a good thing for me to attend, and would be helpful to carry on the research further in this topic. So just an introductory course, but really I came to know a lot of things. And most importantly, I would be very thankful to you, sir, like Dr. Chinapat, sir. Like this is the first time I am seeing work which would be published in Nature or Acta Materia, which has a lot of impact factor, like nearly 20 or 28, and it's really a big thing for Indian researchers to like know how the work should be, the quality of work and the quantity of the work which should be there for the Nature or Acta Materia, which are like high impact factor journals. So that is the second thing which I want to be thankful for him. And yeah, and the accommodation here was really good at NIT Warangal, and the reception was also very good. So I would be very thankful for that. And regarding Professor Ravi Kumar sir, I think he has also done a great job on implant side, and it was really good to see those new like implant from the implant point of view, like the scanning part and the modeling part and the difficulty in like doing surgical implants. So I'm really like it was a great and wonderful experience attending this session. Yeah, thank you.
Good afternoon, sir. I'm Neeraj. Good afternoon, sir. I'm Neeraj. I'm from IRCAT Indore, working as a scientific officer there. So in our lab, we have these facilities. We have PBF, we have DD, but we have not touched the simulation part yet. We are working on multi-materials. We have also made some copper nickel tubes for thermoelectric generator, but we cannot predict all these properties, how the crystal plasticity will grow, how the diffusivity will work. I guess your talk will give us a guidance to how to work on these things. And also we have signed some MOUs with ISRO also, so that will also help us. Thank you so much. That's all.
Now the Dean IRA and GIAN local coordinator Professor S. Srinivasarao garu to reflect on the feedback and
Good afternoon to all. So special thanks to Professor Chinnapat. He has shown a lot of interest to come all the way from UK and has delivered nice lectures. His interaction with me is very nice. He is so friendly, and he has taught. You are very happy with his lectures, I think, all these 5 days. We know this additive manufacturing is the order of the day. Modeling, simulation, as well as manufacturing process is very much essential for particularly for mechanical engineers. We all know that additive manufacturing helps a lot. Material wastage will be reduced and reliability is going to increase, and precise products will be obtained. For that, lot of modeling, simulation, identification of composition, lot of things may be there behind that. Finally, we are getting the product with a precise, very much finished product. For that, lot of technologies has to be learned. So all those things might have got exposed to by exposed to these topics by interacting with him and with his lectures. So I thank coordinator for proposing this course and interacting with foreign faculty, for submitting to Government of India, for getting accepted and conducting the course physically. Nowadays, conducting course physically is because of the corona and all, we got lot of gap. Previously, courses are conducted physically. After, during corona and after corona, everybody is expecting that they want to listen from their home, and nobody wants to come out. Everybody expects that I can get a lesson, I can listen the lectures, and I can without moving from my workplace, I can get lot of knowledge. But this type of physical interaction will give a lot of exposure. You can interact with the people who are working in the same area and coming all the way from different parts of the country and staying for 5 days at one place and discussing with foreign expert. Lot of knowledge transfer will happen with this type of physically attending the lectures. I thank all the participants for showing interest to apply, and I once again thank all the administration of your institution for sponsoring physically to attend these courses. So special thanks once again to Professor Chinnapat. He is having lot of expertise in his area for the interest and research areas. With his interaction, you not only for these 5 days, in future also you can interact with him, and he can give a lot of guidance for doing any research collaborations or interaction with you, and the knowledge whatever you have acquired, this it will be definitely transferred from you to your students and your institutions. It will benefit a lot. Government of India, this GAN phase 4 scheme, they are insisting all the lectures should be recorded, and live telecast, live webcast must be there. So all the web links were shared. People who are listening is not only the persons who have physically come to this NIT Warangal, so they have shared web link to all the institutions, and they have shared me also to circulate among faculty and students of NIT Warangal. So we did a lot of things for the benefit of whole society. So many people might have got benefited by listening to his lectures in this country. So I thank Government of India for initiating such a beautiful program and accepting our courses. In this GAN 4 phase 4, we got around 21 courses till now approved, and this course and one more course was started on the same day. Two courses in the GAN 4 phase, two courses started. They are supposed to be completed by March 31st. So all of you can refer our institute website and GAN portal also for forthcoming programs, and which are not relevant to your domain, means you can convey to the appropriate faculty members and students of your institution, so that they can also apply and come to NIT Warangal and make all other programs also a grand success. I wish you all the best to all of you. Thank you once again.
Dr. N. Venkat Ravi Kumar. J. Vinod Kumar. Thank you, sir. Thank you, sir.
So, very good afternoon. So, I would like to give a valedictory function remarks or the address. So, it's my privilege to give a vote of thanks for this valedictory function. So, we would like to thank Government of India, first of all, for financial support under GIAN scheme. And we would like to thank Professor Subudhi, the Director NIT Warangal, for his continuous encouragement, and Professor Channapat from Queen Mary University of London, the international faculty, Professor S. Srinivasarao, Dean IRAA and GIAN local coordinator, participants for the grand success of this program, and the management who deputed them here away from the 5 days and learning about this topic. And we would like to thank Dr. T. Sadasivarao, the faculty in charge of MT section, and we would like to also thank Professor N.V. Umamahesh, registrar in charge, NIT Warangal, and all deans and heads of NIT Warangal, all officers of NIT Warangal, office staff of Mechanical Engineering Department, audio visual support by Mr. Vijay and his team, Lakshmi Photo Studio for live webcasting and video recording, and most importantly, Mr. Srikanth, Mr. Uday, and Mr. Kishore. Give them a big round of applause. And Suma also, the MTech student of Additive Manufacturing. So thank you all. Let us raise for the national anthem. So we have to sing ourselves.